Hello there and welcome to Science for Sleep, a place where curiosity winds down into comfort and science takes the slower road so your thoughts can drift and settle. Tonight we're turning our gaze outward, far beyond the stars above your head, past the familiar patterns of constellations, past the spirals of galaxies, past even the deepest image ever taken by a telescope. The gentle question guiding us tonight is a simple one, though it carries an almost impossible weight. What is on the other side of the universe? It's a question that sounds almost childlike at first, the kind you might have whispered while lying in the grass at night, wondering if the sky ever ends. And in a way it really is a child's question, but one that even the greatest scientists haven't stopped asking. If you walk to the end of your street, there's more street. If you cross a river, there's land waiting. But if you travel far enough into the universe, where do you arrive? Does it have an edge, a boundary? Or does it simply go on without end? These are the thoughts that can keep someone awake at night if they don't come with soft explanations and careful pacing. So let's not rush. We'll take our time to wander gently through them, letting ideas unfold slowly, step by step, without the pressure of needing a final answer. Before we settle deeper into this journey, I wonder something small. Where are you listening from right now? Is it night where you are, or perhaps early morning? Maybe you're already tucked into bed, or maybe you're letting this play while resting quietly in your room. It feels fitting to ask, because when we talk about what's on the other side of the universe, each of us is actually experiencing a slightly different slice of that very universe. Your night sky might hold the same moon as mine, but the stars above you shine from angles and distances I don't see here. Together we're scattered across the world, yet at the same time we share this same question about what lies beyond. If you find comfort in this kind of wandering, if it soothes you or gives you something interesting to hold on to as you drift off, I'd be grateful if you pressed a like on this video or subscribed. It helps this quiet little corner of science reach someone else who might need a soft companion for their thoughts tonight. So now let's ease into the big question. The universe stretches in every direction, and no matter where you point your telescope, you see more galaxies, more light, more stars scattered across distances so enormous they can barely be described. Yet there is a horizon, a limit to what we can see. That limit isn't like a wall or an edge of a table. It's more like the furthest distance light has had time to travel since the beginning of everything. Beyond it, we don't know. Beyond it, we can only imagine. That's the threshold we'll step toward tonight. Slowly, carefully, letting each explanation make room for the next, until the question itself feels less like a mystery to solve, and more like a gentle landscape to wander. The universe feels endless when you look at it. Step outside on a clear night, away from city lights, and tilt your head back. You'll notice at first a few bright stars, then more, then fainter ones filling in the spaces between. The longer you look, the more your eyes adjust, and soon you begin to see that the sky is not empty at all. It's crowded with light, so much that it almost feels impossible that all of it is really out there. If the sky itself is so full, then it's natural to wonder how far it goes. The human brain is used to things having borders. Every field has a fence, every page has edges, every room ends in walls. So when we imagine the universe, the mind wants to treat it the same way. There must be a line where it stops. There must be a border. But when astronomers speak about the universe, they explain that what we think of as an edge is not like any ordinary boundary we've ever touched. The first reason for that is light itself. Every star, every galaxy, every nebula you see is sending out light, and that light takes time to reach you. Even the sun, the closest star, is seen as it was 8 minutes ago, because that's how long it takes for sunlight to travel across the distance between it and Earth. When you look at the nearest large galaxy, Andromeda, the light you see tonight actually left there more than 2 million years ago. In other words, the night sky is already a kind of time machine. You're never seeing things as they are right now, but only as they once were. Because of this, when we talk about the edge of the universe, we don't mean a physical rim or cliff. What we mean is the furthest distance that light has had time to travel since the beginning of the cosmos. Scientists call this the observable universe. It's like standing in a dark field with a lantern. The glow of your light only reaches so far, and beyond that, the darkness remains unseen. But in space, the lantern is time itself, about 13.8 billion years since the Big Bang. Light from beyond a certain distance simply hasn't had enough time to arrive. That doesn't mean there's nothing beyond it. It only means we cannot see it. Imagine inflating a balloon with tiny dots drawn on its surface. As the balloon grows, the dots move farther apart. No matter where you stand on the balloon's surface, it looks as though everything else is rushing away from you. This is what astronomers discovered in the 20th century. The universe is expanding, and every galaxy appears to be moving away. Because of this expansion, the edge we see is not just the distance light could have travelled in 13.8 billion years. Space itself has been stretching as that light has been moving. The real boundary of what's visible is much farther, roughly 46 billion light-years away in every direction. That's the size of the observable universe, a sphere centred on you, and at the same time a sphere centred on me and on every other observer, because no matter where you stand, the horizon looks the same. The strange part is that there is no visible sign when you approach this edge. You won't see a wall or a gap in the stars. As far as the eye or a telescope can tell, the galaxies keep stretching out, smaller, fainter, further, until their light thins into the background. If you were travelling in a spaceship, you would never feel that you'd crossed a line. The edge isn't a place you can visit. It's a limit built into what you're able to observe, a horizon in every direction. For many people, that feels unsatisfying. We like definite answers. When you walk to the edge of a forest, the trees stop. When you reach the shore, the land ends and the ocean begins. But the universe refuses to give us that sort of closure. Instead, it offers a boundary that exists only because of the speed of light and the age of the cosmos. Beyond it, reality continues. We're certain of this, even though we cannot see it, because the same laws of physics that apply here should apply there too. Galaxies are likely scattered across the unreachable stretches just as they are in the parts we can see. Stars are burning. Planets may be circling them. Perhaps there are beings asking questions very much like ours, wondering in their own quiet way what lies on the other side of what they can observe. That thought alone can keep your mind busy. The observable universe is not the whole universe. It's just the patch of sky and matter available to us, determined by time and distance. So, what we call an edge is really a veil drawn by physics. The cosmos could go on infinitely, or it could loop back on itself in ways we can't yet picture. But what we do know is that the part we can see is vast enough to overwhelm. Within that horizon lie hundreds of billions of galaxies, each one holding hundreds of billions of stars. The numbers stack up until they lose meaning, but the important point is this. Even inside our limited view, there is more than we can ever fully take in. The edge reminds us not of emptiness, but of abundance. To make sense of this, scientists have built instruments that stretch our sight farther than human eyes could ever go. The Hubble Space Telescope once aimed at a patch of sky so small it looked empty to the naked eye. After days of gathering faint light, the image revealed thousands of galaxies in that single pinprick of darkness. Later, the James Webb Space Telescope pushed even deeper, collecting light from galaxies formed only a few 100 million years after the Big Bang. Those galaxies are now so far away that their light has been stretched by expansion into longer, redder wavelengths. They sit close to that invisible horizon. Every new improvement in technology pushes the veil back a little further, but no matter how powerful the telescope, there will always remain a point beyond which we cannot see. The universe is simply too vast, and time has been too short for its light to reach us. Some people imagine the edge as being similar to the edge of a map in an old storybook, where sea monsters waited beyond the drawn coastlines. But science is less dramatic and more humbling. The edge we speak of is not dangerous. It's quiet. It's unreachable. It exists only because of limits in the speed of light and the expansion of space. If you could somehow ride alongside that expanding frontier, you would never find a barrier. Instead, the horizon would always move away from you, just as the horizon on Earth moves when you walk toward it. The edge is not fixed. It's not a fence keeping you in. It's simply the maximum distance information has been able to cross since the universe began. That idea leads to another reflection. If the edge is only what we can see, then what lies beyond is not cut off in any physical sense. It's there, continuing in whatever form the universe takes. Some scientists suggest that the universe may be infinite. In that case, beyond the observable horizon lies an endless stretch of more of the same. If the universe is finite but unbounded, it might curve back on itself, like the surface of a sphere. In that case, travelling far enough in one direction could in theory bring you back to your starting point, though distances are so unimaginably large that no traveller could ever test it. Either way, the edge is not the end. It's just a marker of how far our light has travelled and how far our instruments can reach. This is one of the most difficult ideas for the human brain to settle into. We want beginnings, middles, and ends. We want closure. But the universe operates on scales where those instincts break down. The edge we cannot see is not the end of space, but only the end of knowledge. Beyond it, reality continues silently. That continuation might mirror what we see here, or it might hold surprises our theories can't yet predict. For now, the best we can do is acknowledge the boundary, respect it, and keep building ways to peer just a little farther. And while the instruments of science keep searching, there is something oddly comforting about the fact that there will always be a horizon. Just as the ocean horizon makes a voyage feel vast, the cosmic horizon reminds us that there is always more waiting in the darkness, whether we can measure it or not. It leaves room for wonder, and perhaps that wonder is as important as the knowledge itself. The universe doesn't give us edges like walls. It gives us horizons like invitations, places where curiosity can stretch out even if our eyes cannot. When you look at the sky, it seems still. The stars appear fixed in their places, the constellations unchanged from year to year, the patterns steady enough that ancient civilizations used them as guides for navigation, planting, and storytelling. But what we cannot sense with our eyes in a single lifetime is that everything above us is in motion. Galaxies are not frozen. They're gliding, drifting, moving away from one another across space itself. The universe is expanding, and that expansion is not like anything in our ordinary experience. It is not as though galaxies are flying through empty space the way sparks scatter from a fire. Instead, the very fabric of space is stretching, carrying galaxies with it. The first clues of this came in the early 20th century. Astronomers using telescopes noticed that the light from distant galaxies was shifted toward the red end of the spectrum. This shift, known as redshift, is what happens when a source of light is moving away from you. It is similar to how the sound of a siren changes pitch as an ambulance passes by, higher when it approaches and lower when it moves away. The same principle applies to light. When galaxies are retreating, their light stretches, shifting to longer, redder wavelengths. One astronomer, Edwin Hubble, gathered these observations and realized something extraordinary. The more distant a galaxy was, the more its light was shifted. In other words, galaxies farther away were moving away faster. This wasn't just random motion. It was systematic, consistent, and it meant that space itself was expanding in every direction. To picture this, the balloon analogy helps again. Imagine small dots drawn on the surface of a balloon. As you blow it up, the dots move apart from one another. Each dot sees all the others receding, and the farther away a dot is, the faster it seems to retreat. No dot is the centre. Every point shares the same perspective. In much the same way, no matter where you are in the universe, expansion looks the same. There is no special vantage point, no privileged centre. Space itself is stretching, and everything embedded in it is carried along. This realization overturned centuries of thought. For much of history, the universe was assumed to be static and eternal. It simply existed, vast and unchanging. But expansion implied a beginning, a time when all the galaxies were closer together, a time when everything we see now was once compressed into a smaller, hotter, denser state. This led to the idea of the Big Bang, the moment when the universe as we know it began expanding from an initial condition almost beyond comprehension. It is important to note that expansion does not mean galaxies themselves are swelling, or that solar systems are stretching apart. The forces that hold stars together, that bind planets to their orbits, are far stronger than the pull of cosmic expansion. Instead, expansion happens on the grandest scales, in the distances between clusters of galaxies. Within galaxies, gravity dominates. Between them, space stretches. This is why the Milky Way and the Andromeda Galaxy are actually on a collision course. Their mutual gravity overcomes the general expansion, and billions of years from now, the two galaxies will merge into a new, larger system. On larger scales, however, expansion wins. If expansion was simple, the story might end there. But the universe is rarely simple. Over the decades, scientists tried to measure whether expansion was slowing down. Gravity, after all, is attractive. It pulls matter together. If the universe began expanding in the Big Bang, then gravity should gradually slow the rate of that expansion, perhaps even stop it, and cause a collapse. The ultimate fate of everything would depend on how much matter there was, and how strongly gravity could counteract the outward momentum. For years, this was the central question. Would the universe expand forever, gradually cooling into darkness? Or would it one day halt and reverse, collapsing into a final crunch? The debate seemed endless, until new observations revealed something completely unexpected. Instead of slowing, the expansion of the universe is speeding up. Galaxies are not only retreating, they're retreating faster over time. The cause of this acceleration is something scientists call dark energy. It is not energy in the ordinary sense, like the heat of a flame or the electricity in a wire. It is a property of space itself, an energy that seems to push outward, counteracting gravity on the larger scales. Its nature is still mysterious, but its effects are unmistakable. Distant supernovae used as cosmic yardsticks revealed that galaxies billions of light years away are moving faster than they should be if expansion was slowing. The only explanation is that something unknown is driving them apart more forcefully than gravity can pull them together. Dark energy now makes up the majority of the universe's energy budget. Matter, the stuff of stars and planets, is only a small fraction. Most of what exists is invisible, not because it is hidden behind clouds of dust, but because it is fundamentally different from the forms of energy and matter we know. This means that when we ask what's on the other side of the universe, part of the answer lies in understanding how expansion will shape what lies beyond our current horizon. If expansion continues to accelerate, regions of the universe now visible will eventually slip beyond our reach. The light they emit will stretch until it can no longer reach us. Over unimaginably long timescales, more and more of the cosmos will drift into invisibility, not because it disappears, but because space grows so rapidly that its signals can no longer catch up. This paints a picture of a universe where the observable portion is temporary. What we see now is a snapshot. Billions of years from now, observers in distant futures will see fewer galaxies, not because they are gone, but because they have moved forever out of sight. For them, the universe may appear emptier, quieter, lonelier. They may never know, just by looking, that other galaxies ever existed. Only we, living now in this cosmological era, can still catch sight of them. The expansion is not uniform everywhere either. On local scales, galaxies bind into groups and clusters. The Milky Way belongs to a small group with Andromeda and a handful of dwarf galaxies. Beyond that lies the Virgo cluster, and still farther, superclusters that weave into a cosmic web. These structures are immense, but they are islands within the sea of expansion. Gravity holds them together, even as the overall fabric of space stretches. One of the most remarkable aspects of expansion is that it allows us to trace the universe back to its beginnings. By measuring the current rate of expansion, known as the Hubble constant, and extrapolating backward, we can estimate the age of the cosmos. Combined with observations of the cosmic microwave background, the faint afterglow of the Big Bang, we arrive at the figure of about 13.8 billion years. This is the time since space began to expand, since the universe began to cool and evolve into the structures we now see. But the deeper we look, the more complex the story becomes. Different teams measuring the expansion rate with different methods have arrived at slightly different numbers. One set of techniques using nearby galaxies and supernovae gives a higher value. Another, using the cosmic microwave background, gives a lower one. The disagreement has persisted, suggesting that there may be something missing from our understanding of cosmic history. Perhaps new physics is waiting to be discovered. Perhaps dark energy is not constant but changes over time. These open questions remind us that the universe is still revealing itself. Expansion is not just a fact, it is an active area of discovery, a puzzle that scientists continue to refine. It can be difficult to imagine what expanding space actually feels like. We often picture galaxies flying through emptiness, but that image misses the essence. Expansion is not motion through space, it is the growth of space itself. The distance between two galaxies increases because the fabric of the universe stretches. There is no outside into which it expands. The universe is not like a balloon filling up within a larger room. It is more like the surface of the balloon itself, which grows without needing anything around it. This is why asking what the universe expands into is tricky. It expands into nothing external. The expansion is of the universe itself. What's even stranger is that this expansion has no centre. Wherever you stand, it looks as though everything else is moving away. This is why it is misleading to think of the Big Bang as an explosion from a single point in space. It was the beginning of space itself, everywhere at once. Every region is equally central. Every observer, no matter where they are, sees the same pattern of expansion. This has profound implications for how we think about what lies beyond. If the universe is infinite, expansion means that it is infinite now, and always has been, only stretched thinner. If it is finite but unbounded, expansion means that its size grows but still has no edge. Either way, the picture is not one of limits but of ongoing growth, carrying with it the galaxies, the clusters, the stars, and perhaps countless regions we will never know. For a moment, it's worth considering how expansion connects back to us here on Earth. The light from distant galaxies, stretched by expansion, eventually arrives at our telescopes. It tells a story written over billions of years. Without expansion, that story would be very different. The sky might not be filled with such variety. The history of stars forming, dying, and spreading heavy elements across space would not have unfolded in the same way. The very atoms in your body, the carbon, oxygen, iron, were forged in stars long ago, scattered by explosions, and gathered into new clouds that became the solar system. Expansion gave room for that cycle to play out. Without it, the cosmos might never have grown complex enough to include us. And so, when we ask what lies on the other side of the universe, we cannot separate the question from expansion. It is expansion that creates the horizon, expansion that defines what is visible, expansion that ensures there is always more beyond our reach. It is not a static edge, but a shifting boundary, always retreating, always carrying new mysteries just out of sight. When astronomers speak of the cosmic horizon, they are not talking about a physical boundary you could ever approach in a ship. They mean the farthest distance from which light has had time to reach us since the universe began expanding. Imagine standing on a beach and looking out to sea. The water stretches on until it meets the sky. At that point, your eyes can go no further. You know the ocean continues, but the horizon marks the limit of what you can see. The cosmos has a similar line. It is not drawn in the sand or marked by a ridge of rock, but by the age of the universe and the speed of light. Beyond it, there may be more galaxies, more stars, more structures, but their light has not had enough time to travel across the vastness to meet our gaze. This horizon is sometimes called the particle horizon. It represents the maximum distance from which particles of light could have travelled to us since the Big Bang. Because the universe is about 13.8 billion years old, you might expect the horizon to be about 13.8 billion light-years away. But that is not the case. Space itself has expanded while the light was travelling, stretching distances far greater. The actual radius of the observable universe is around 46 billion light-years. That means the diameter of the sphere we can see is about 93 billion light-years across. It is an immense volume filled with hundreds of billions of galaxies, each with their own stars, planets, and perhaps even forms of life we can only imagine. The important thing to realise is that this horizon is not fixed. It changes with time. Billions of years ago, the cosmic horizon was smaller. Less of the universe was visible because light had not had enough time to cross the gaps. Billions of years from now, the horizon will be larger, and new regions will come into view. But because expansion is accelerating due to dark energy, there is a strange twist. Many galaxies that are visible today will one day slip beyond our reach. Their light stretched until it can no longer reach us. At the same time, distant regions beyond our current horizon may never become visible, no matter how long we wait. Expansion is faster than the speed at which light can close the distance. This creates an ultimate limit, not just of what we see now, but of what we will ever be able to see. To get a sense of what this means, consider a galaxy near the edge of visibility. Its light is faint, stretched into the infrared part of the spectrum. Our telescopes, especially ones like the James Webb Space Telescope, are designed to pick up this stretched light. But in the far future, that same galaxy will no longer send signals that can reach us. Space will grow between us too quickly. The galaxy will still exist, still shine, still move through its own part of the universe. But for us, it will have slipped away forever. This is not an illusion, or a trick of distance. It is a real effect of cosmic expansion. The horizon is a shifting, dynamic line that governs the limits of knowledge. The cosmic horizon also has another meaning. Beyond the limit of visible galaxies lies the relic light of the Big Bang itself. When the universe was about 380,000 years old, it cooled enough for atoms to form, and light was suddenly able to travel freely. That light has been moving through space ever since, stretched by expansion into microwaves. Today we detect it as the cosmic microwave background, a faint glow spread evenly across the sky. This background is like a wall behind which we cannot see with ordinary light. It represents the farthest back in time our telescopes can look. Anything earlier than that is hidden, because the universe was opaque before atoms formed. In this sense, the cosmic microwave background is another horizon, not in distance, but in time. When scientists map this background radiation, they see small variations in temperature, tiny fluctuations that reveal the seeds of galaxies and clusters that would form billions of years later. These maps give us a snapshot of the universe in its infancy, an almost baby picture of the cosmos. It is humbling to realise that the furthest we can look back is not to the Big Bang itself, but only to this surface of last scattering, the point when light could first travel. Beyond it, the universe is hidden, veiled by its own early density and heat. The cosmic horizon, then, is not just about how far we can see outward in space. It is also about how far we can see backward in time. It is easy to assume that horizons are frustrating, that they represent limits. But in practice, horizons are what give us a frame of reference. Without them, we would be adrift with no sense of scale. The cosmic horizon tells us that the universe has a history, that it has an age, that it is finite in what we can observe even if it is infinite in extent. The very fact that we can define such a horizon is one of the triumphs of modern cosmology. For most of human history, people could only guess at the size of the cosmos. Some thought it ended with the stars. Some imagined crystal spheres surrounding the Earth. Now we know that what we see is only a portion, bounded not by glass or stone, but by time and physics. And yet the horizon also carries a certain emotional weight. To know that beyond the limit of sight lies more, unreachable and unseen, is both awe-inspiring and unsettling. There are galaxies out there whose light will never reach us, civilizations that, if they exist, will remain forever unknown. The horizon separates us not just from empty space, but from the possibility of contact. It means that no matter how advanced our instruments become, no matter how long we wait, the universe will always hold secrets beyond reach. This is not a failure of science. It is a property of the cosmos itself. For those who wonder what is on the other side of the universe, the horizon is a reminder that there may be no single answer. The other side could be more of the same. More galaxies, more stars, more matter spread across expanding space. Or it could hold something unexpected, some structure or phenomenon we have not yet conceived. The horizon does not tell us what is beyond. It only tells us that there is a beyond. And perhaps that is the most important part. It is worth pausing to consider how this compares to the horizons we know on Earth. When you look across the ocean, the horizon is simply the limit of your sight. Sail a little farther, and more becomes visible. On land, climb a mountain, and the horizon stretches outward. But the cosmic horizon is different. You cannot travel to it. No matter how fast you go, it recedes. Because it is defined by light and time, not by distance alone, it will always move away as you approach. This makes it unique among horizons, a line you cannot cross. It exists not as a destination, but as a boundary of perception. Scientists sometimes describe the observable universe as a bubble centered on each observer. Your bubble is 46 billion light-years in radius. So is mine. They overlap, but they are not identical, because light reaches us from slightly different regions. In principle, there are regions of the universe that I can see but you cannot, and vice versa depending on our exact positions. Multiply this across all observers in all places, and the cosmic horizon becomes not one sphere but countless overlapping ones, each unique to its viewer. The universe is stitched together by these spheres of perception, each one a window into a different slice of reality. This leads to a subtle but important point. The horizon is not an edge of the universe itself. It is only an edge of what is visible to us. Beyond it, the universe continues, perhaps endlessly. This distinction is crucial. When people ask if the universe has an edge, the answer is that the only edge we know is the one defined by our view. The universe itself may have no edge at all. It may curve back on itself, or it may go on without end. The cosmic horizon is not a wall. It is a reminder of how limited we are, and how much more there could be. The more you think about this, the more it shapes how you understand your own place in the cosmos. Every point in space has its own horizon. An alien in a distant galaxy would have its own sphere of visibility centered on itself. What lies beyond our horizon may be visible to them. What lies beyond theirs may be visible to someone else. In this way, the universe is like a vast tapestry in which no single observer can ever see the whole. Each of us has a partial view, a fragment of the whole picture. Together, these fragments suggest something larger than any one of us can comprehend, and while that might sound frustrating at first, there is something gentle in it too. It means that the universe is never exhausted, never fully known. There will always be more to imagine, more to wonder about, more to ask. The horizon is not a barrier to curiosity. It is what makes curiosity possible. Knowing that there is a line beyond which lies mystery keeps us asking questions, keeps us building better instruments, keeps us humble about our place in the vastness. The cosmic horizon, then, is not only a scientific concept, it is also a philosophical one. It tells us that knowledge has limits, not because we are lazy or careless, but because the universe is structured that way. It tells us that our lives are lived within boundaries we cannot cross, yet those boundaries are themselves evidence of something larger. It is a paradox of sorts. The very fact that we cannot see beyond makes us certain that there is a beyond. The horizon hides, and in hiding it reveals. When you see the stars above you, what you're really seeing is the story of light that has been travelling for a very long time. Every point of brightness in the night sky is not the present state of a star, but its past. The twinkle that reaches your eyes tonight may have begun its journey long before human beings even existed. The light from the closest star beyond the Sun, Proxima Centauri, takes a little more than 4 years to arrive. That means when you look at it, you are looking back 4 years into history. The distance is small in cosmic terms, but even that short span reminds us that sight is never immediate in the universe. Everything is delayed, everything arrives from some earlier time. Extend the thought farther, and it becomes more striking. The light from the Andromeda Galaxy is over 2 million years old. When it left, Earth was inhabited not by modern humans, but by early ancestors who had not yet discovered many of the tools and languages we take for granted. While they were shaping stone or wandering through landscapes untouched by cities, the light began moving, crossing empty space, photon by photon, until finally tonight it reaches you. Every time you raise your eyes to the galaxy, you are sharing a connection with beings who lived countless generations ago. Now stretch the thought even further. The faintest galaxies visible to our deepest telescopes are so far away that their light has been on the road for more than 13 billion years. That means the beams entering an instrument like the James Webb Space Telescope tonight were first released when the universe was only a few 100 million years old. Stars were just beginning to form. Galaxies were smaller and more chaotic. Structures that now appear vast and orderly were then only clouds and clumps. And yet those first bursts of light have kept travelling, undisturbed, until we developed the means to catch them. In this sense, astronomy is less about looking outward and more about looking backward. Every observation is a time machine. The journey of light is shaped not just by distance, but by the medium it crosses. In space, the medium is mostly vacuum, but it is not perfectly empty. Along the way, photons can pass through clouds of gas, through fields of dust, through the gravitational wells of massive objects. These encounters alter their path. Gravity can bend light, a phenomenon known as gravitational lensing. When light from a distant galaxy passes near a massive cluster, its trajectory curves, and we see the galaxy's image distorted or magnified. In this way, light's journey is not always straight, but bent and twisted by the weight of matter. For astronomers, this is not a problem but a tool. The bending reveals the presence of matter we might not otherwise detect. Some of that matter is visible. Some of it is dark matter, invisible to direct observation, but revealed by the way it bends light on its long journey. Dust also plays its part. Within galaxies, clouds of dust scatter and absorb certain wavelengths, making stars appear redder or dimmer. To correct for this, astronomers must carefully measure how light has been filtered along its path. What finally arrives at a telescope is not exactly what was emitted. It is a record altered by billions of years of interactions. Reconstructing the original signal requires careful study, but the effort reveals not only the distant source, but also the intervening space. In other words, light is both messenger and map. One of the most dramatic aspects of light's journey is how expansion stretches it. As space itself expands, the wavelength of light travelling through it also stretches. What may have begun as ultraviolet or visible light can arrive billions of years later as infrared or even microwaves. This is why the glow of the Big Bang is seen today, not as a blinding flash, but as faint microwave radiation spread evenly across the sky. The light itself has cooled during its journey, redshifted by expansion. When astronomers measure this stretching, they can estimate how far and how long the light has travelled. The greater the redshift, the farther back in time we are looking. This stretching creates an odd situation. There are galaxies whose light is reaching us now, but because of acceleration, they're already moving away faster than the light can close the gap. That means the light we see is the last we will ever receive. Once it passes, the galaxy will slip permanently beyond our horizon. From our perspective, it will fade into invisibility, even though it continues to exist. Light's journey, in this case, is a one-time gift. Once given, no more can follow. Think for a moment about the scale of time this involves. A photon leaving a star in a distant galaxy billions of years ago might have travelled through expanding space without interruption for all that time. During its trip, entire species on Earth have risen and vanished. Continents have shifted. Ice ages have come and gone. Civilizations have grown, fallen, and left ruins. Through it all, the photon kept moving, undistracted, until at last it found its way to a detector on Earth. That moment is fleeting. The photon is absorbed, its journey ends, and its story becomes part of our knowledge. Multiply this by the countless photons arriving every second from all parts of the sky, and you realize that astronomy is built on these tiny patient travelers, each one a sliver of ancient history. Light's journey is also uneven. Shorter wavelengths, like gamma rays and X-rays, can be blocked by Earth's atmosphere, which is why telescopes studying them must orbit in space. Longer wavelengths, like radio waves, pass through more easily, and can be studied from the ground. Different bands of light reveal different aspects of the universe. Radio waves show us cold gas clouds. Infrared reveals star-forming regions hidden by dust. X-rays expose the hot gas around black holes. Every type of light tells a part of the story, and together they create a fuller picture of what has happened during its long journey. There is a quiet elegance in realizing that light has been our most faithful guide. Before we had instruments, we had eyes, and even then, light carried information across unimaginable distances to fall on our retinas. The same photons that travelled across space interacted with the molecules in your eye, triggering signals in your brain and letting you see the stars. The same process happens with telescopes, only extended into ranges our eyes cannot detect. All of it depends on light completing its long trip. Without those photons, the universe would remain invisible. The story becomes even more remarkable when you remember that light is not only ancient but also fast. Nothing moves faster. At about 300,000 kilometers per second, it seems impossible that it could take billions of years to cross the cosmos. Yet the distances are so great that even light at that incredible speed needs eons. If you shine a flashlight toward the moon, the beam takes a little more than a second to arrive. A signal to Mars might take anywhere from 4 to 20 minutes, depending on orbits. To Pluto, several hours. But to cross the Milky Way, one photon must keep travelling for about 100,000 years. And to cross from the edge of the observable universe, it takes billions. Speed is enormous, but space is larger still. This is why light's journey is also a measure of time. When scientists speak of look-back time, they mean exactly this: the number of years the light has been travelling. A galaxy with a look-back time of 10 billion years is one whose light left 10 billion years ago. We see it not as it is, but as it was. For some galaxies, the gap is so wide that what we see may no longer exist in the same form. Stars may have burned out, structures may have shifted, but the image remains frozen in the light that began its journey long ago. Astronomy, then, is an archive of ancient snapshots, preserved not in books or stones, but in beams crossing space. There is another layer to this, one that connects directly to human perception. The light that has travelled for billions of years does not arrive as a flood, but as a trickle. Photons are sparse by the time they reach us, spread thinly over immense areas. To gather them, telescopes must collect patiently, sometimes for hours or days, to build an image. The famous Hubble Deep Field, one of the most striking images of the distant universe, was created by pointing the telescope at a seemingly empty patch of sky and holding the shutter open for days. Gradually, enough photons arrive to reveal thousands of galaxies. Each faint speck in that image represents light that has been journeying across space for most of cosmic history. Without that patience, without the willingness to wait, the story would remain hidden. In this way, light's journey mirrors our own search for understanding. It is not quick, It is not simple. It requires waiting, gathering, interpreting. But the reward is immense. Every photon carries not just brightness, but information about its source, its temperature, its composition, its motion. By splitting the light into spectra, astronomers can read these details like lines of a code. The long journey of each photon becomes a message, not only about where it came from, but about everything it passed along the way. If you pause to think about it, you're surrounded right now by this invisible rain of ancient messengers. Even if you are indoors, light is still reaching the Earth from every corner of the sky. It falls on the atmosphere, it bounces, it enters your room. The photons striking the ground outside tonight may have been travelling since before the solar system formed. They complete their journey quietly without fanfare, arriving at a planet that only recently developed eyes and instruments to notice them. The scale of patience involved is almost beyond imagination, and yet it is happening constantly. In the end, the question of what lies on the other side of the universe is inseparable from the question of how light travels to us. Without its long journey, there would be no edge to speak of, no horizon to measure, no expansion to trace. The entire story of the cosmos comes to us through the persistence of these tiny particles, moving faithfully across time. Each one is a witness to history, and together they allow us to piece together where we are and what lies beyond. When people talk about the universe, they often picture everything that exists as though it were laid out in front of us like a giant map. It feels natural to think that if you had a powerful enough telescope, you could simply keep zooming in until you saw it all. But the reality is very different. There is a line between what we can observe and what we cannot, a separation that is not made by walls or barriers, but by the laws of physics themselves. The observable universe is only a fraction of what exists. Beyond it lies the unobservable, regions that are real, but forever hidden from us. The reason for this separation begins with light. As we've already seen, the universe has a finite age, about 13.8 billion years. Light, though incredibly fast, still takes time to travel. That means we can only see as far as light has had time to reach us. Anything farther away is invisible, not because it isn't there, but because its signals have not had enough time to arrive. This defines the observable universe, the sphere of space from which light has reached Earth since the beginning. Beyond that sphere lies the unobservable, places whose light is still on the way, or perhaps whose light can never arrive because expansion carries them away faster than light can close the gap. It is important to stress that the unobservable universe is not a blank void. It is not an edge of existence. It is simply a region cut off from us by time and distance. If you could magically transport yourself beyond the horizon, you would find galaxies, stars, perhaps even planets and life. To any observer in that region, their own observable universe would stretch around them just as ours does around us. What is unobservable to us is observable to them. Each point in space has its own sphere of visibility, and together those spheres overlap and cover the whole. The unobservable is only relative to where you stand. This idea can be difficult to settle into because our instincts tell us that what we cannot see may not exist. But science has shown again and again that the universe is not limited to what falls within our senses. We cannot see infrared light with our eyes, yet it is real and measurable. We cannot hear ultrasound, yet bats and dolphins use it constantly. The same principle applies on cosmic scales. The observable universe is what our instruments can reach, but the unobservable is simply the rest, no less real, only beyond our reach. The divide between these two realms has consequences for how we think about the universe as a whole. For example, when cosmologists try to describe the shape and size of the universe, they must acknowledge that they're working with only a piece of it. The observable part may suggest that the universe is flat and homogeneous, meaning it looks similar in all directions. But what lies beyond could be different. Perhaps space curves back on itself. Perhaps there are regions with different properties, different densities, maybe even different physical laws. We cannot know directly, because those regions are outside our horizon. We can only make educated guesses based on what we see here. The observable universe is itself already vast beyond comprehension. With a radius of 46 billion light-years, it contains hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars. Around those stars are countless planets, moons, and smaller bodies. Multiply those numbers, and the total reaches heights that are almost impossible to grasp. And yet this immensity is only the visible portion. The unobservable universe could be far larger, perhaps infinite. If that is the case, then what we see is like a drop in an endless ocean. One way to imagine this is to think of standing in a forest with fog surrounding you. The fog limits how far you can see, but you know the trees do not stop at the edge of visibility. They continue, stretching farther than your eyes allow. The universe works in much the same way. The fog in this case is not mist but time and expansion. Our view is bounded, but the forest continues endlessly beyond. The unobservable is that unseen continuation. Some scientists speculate that the unobservable may contain regions very much like our own, with galaxies, stars, and perhaps life that evolved under similar conditions. If the universe is infinite, then there could even be regions where matter is arranged in patterns identical to ours. In such an infinite cosmos, there could be another Earth, another you, living a life almost the same but with small differences. This is not science fiction, but a consequence of mathematics applied to infinity. However, because those regions are unobservable, we can never confirm or deny their existence. They remain possibilities rather than facts. The unobservable is also connected to the idea of inflation, the theory that in the earliest fractions of a second after the Big Bang, the universe expanded at an astonishing rate. Inflation explains why the universe looks so uniform on large scales, why the cosmic microwave background is nearly the same in every direction. But inflation also implies that what we see is only a patch of a much larger whole. Like a small window in a vast building, our observable universe is just a section of a greater structure. Beyond it, the unobservable stretches indefinitely. This creates a strange relationship between knowledge and ignorance. On the one hand, we can measure and map the observable universe in great detail. On the other, we must admit that the majority of the cosmos is hidden. Our instruments, no matter how advanced, cannot break through the limits of light and expansion. Even if we built perfect telescopes, even if we waited billions of years, some regions would remain unreachable. The unobservable is not just temporary darkness, it is permanent. And yet this does not make the pursuit of knowledge pointless. Quite the opposite. By studying the observable, we can infer properties of the unobservable. For example, by measuring the distribution of galaxies in our region, we can deduce that similar structures likely exist elsewhere. By mapping the cosmic microwave background, we can learn about conditions beyond our direct view. The unobservable may never be seen, but its shadow influences what we can see. In this sense, it is not completely unknown. It leaves traces. This distinction also raises philosophical questions. If something is forever unobservable, can we meaningfully say it exists? For scientists, the answer is yes, because the laws of physics that describe our region should apply universally. There is no reason to think they stop at the edge of the observable. Just as the forest continues beyond the fog, the universe continues beyond the horizon. The unobservable is not absence, it is simply beyond our perception. The boundary between observable and unobservable is not sharp in the way we might expect. There are galaxies right at the edge, whose light is stretched into faint signals barely reaching us. Some of these galaxies may already have crossed into the unobservable, meaning the light we are now seeing is the last we will ever detect from them. In this way, the line between the two regions is dynamic, always changing. With time, more galaxies slip across. What is observable today may become unobservable tomorrow, at least on cosmic timescales. The universe is not static. The boundary moves, shaped by expansion. This moving boundary means that future astronomers will live in a different sky. Billions of years from now, most distant galaxies will no longer be visible. Only the local group, bound by gravity, will remain. Observers in that distant future will look up and see a universe that seems smaller, emptier, and perhaps they will not know the full story. They may not realise that beyond their unobservable lies a vastness filled with galaxies, hidden forever. We live in a unique moment in cosmic history, when the observable universe is still wide and full, when light from faraway galaxies is still reaching us. This is a privilege of timing, a chance alignment of age and visibility. The contrast between observable and unobservable also reminds us of our limitations. Human beings often pride themselves on progress, on building tools that extend our senses. But the universe humbles us by showing that no matter how advanced we become, some truths will remain beyond reach. The unobservable is a reminder of humility, a lesson that the cosmos is not ours to conquer, but ours to glimpse. Our place is not at the centre, but within a horizon that defines how much we can know. Yet there is comfort in this as well. To know that the universe continues beyond what we can see is to know that it is larger than our concerns, larger than our troubles, larger even than our species. The unobservable gives us perspective. It reminds us that our lives, though small in comparison, are part of a greater whole. We're connected not just to what is visible, but to what is invisible, to the unseen stretches of the cosmos that will never touch us directly. In the end, the difference between observable and unobservable is not a difference in reality, but a difference in access. One is the part we can measure, the other is the part we cannot. Both are equally real, equally part of the cosmos. The line between them is drawn not by the universe, but by our position in time and space. Move to another vantage point and the line shifts. Wait long enough, and the line changes. But there will always be a line. There will always be a horizon separating what we can reach from what we cannot. When we wonder about the other side of the universe, we are really asking about the unobservable. What lies beyond the limits of our sight? The answer is that it is still the universe, still real, still governed by the same laws. We may never see it, but we know it continues. The distinction is not between something and nothing, but between the seen and the unseen. And in that distinction lies both mystery and meaning, a gentle reminder that knowledge has boundaries but existence does not. When people think about the universe, one of the most natural questions is whether it has an end. Every journey we take on Earth eventually brings us to a border. Roads reach a finish, rivers flow into seas, mountains level into plains. So it feels intuitive to ask where the universe stops. If you travelled far enough in one direction, would you eventually hit a wall? Would you fall off into nothingness, or find a boundary you cannot cross? The human brain wants things to be bounded. Infinity is not something we experience directly in daily life, so it always feels abstract. But when we look at the evidence from astronomy, the answer is more subtle. The first thing to recognise is that we don't see any edges in the sky. No matter where you look, galaxies appear, scattered more or less evenly in all directions. With better telescopes, faint galaxies appear behind the bright ones, and beyond those still fainter. The pattern does not seem to thin out in any preferred direction. There is no sense that one side of the sky is closer to a boundary than another. This suggests that the universe is homogeneous on large scales. That doesn't mean every patch of sky looks identical, but averaged over great distances it does. There is no privileged centre and no obvious border. This leads to the possibility that the universe is infinite. If so, then it truly has no end. Galaxies stretch outward forever, stars keep forming endlessly, and space continues without limit. Infinity is difficult to picture, but mathematically it is consistent with our observations. If the universe is flat in its geometry, as current data suggest, then it could indeed be infinite in extent. That means that no matter how far you go, there is always more. More galaxies, more stars, more planets, a cosmos without end. But infinity is not the only possibility. It could also be that the universe is finite but unbounded. This is a concept that takes some patience to absorb. A good analogy is the surface of the Earth. The surface is finite. You can measure its area, calculate its volume. Yet if you set out walking in one direction, you never find an edge. You circle back eventually to where you started. The Earth's surface is finite but has no boundary. In the same way, space could be curved back on itself. If that is the case, then the universe might be finite in volume, but you would never find an end. Travel far enough, and you might return to your starting point, just as a traveller sailing across the globe eventually returns to their harbour. Determining whether space is infinite or finite is a major question in cosmology. Observations of the cosmic microwave background give us clues. They suggest that the universe is flat to a high degree of precision. If it is flat, then it could be infinite. But there is a caveat. Space could be so large that even if it is curved, the curvature is too slight for us to detect. It would be like standing on a vast plain. To your eyes, the land looks flat, but in reality, the Earth beneath you is curved. Our observable universe may be too small a sample to reveal the curvature, leaving us unable to distinguish between infinite and merely very large. If the universe is infinite, then the implications are profound. It means that everything that can exist does exist somewhere, repeated endlessly. Somewhere there are galaxies almost identical to ours, with stars and planets arranged in familiar ways. Somewhere there could even be another Earth, with another version of you living a life nearly the same but with small differences. This is not science fiction, but a consequence of infinity. In an infinite space, all possible arrangements of matter eventually occur. It is a strange and unsettling thought, but also one that follows from the mathematics. If the universe is finite but unbounded, the implications are different. In that case, the cosmos has a specific size, even if enormous. You could, in theory, measure its total volume, but because it has no edges, you would never encounter a boundary. The geometry would wrap back on itself. Some models suggest this could create multiple images of the same galaxy in different parts of the sky, as light circles around. Scientists have searched for such repeating patterns in the cosmic microwave background, but so far none have been found. That does not rule out the possibility, only that if space is finite, its size must be much larger than the observable universe. Another layer to the question is time. Even if space is infinite, the future of the universe depends on expansion. As we have seen, the expansion is accelerating, driven by dark energy. That means that galaxies will drift farther and farther apart. Over unimaginable stretches of time, they will cross beyond one another's horizons. Stars will exhaust their fuel, collapse into remnants, or explode into supernovae. Black holes will dominate, then slowly evaporate over timescales so vast they defy comprehension. If the universe has no end in space, it still has a trajectory in time, one in which structures dissolve and energy thins into uniformity. In that sense, even a universe without spatial limits has a kind of temporal story, with stages and outcomes. But the phrase, without end, can be misleading. It suggests permanence, yet cosmology reminds us that everything changes. Galaxies merge and evolve, stars are born and die. Even space itself expands and transforms. A universe without end in space is not static or eternal in the way ancient philosophers once imagined. It is dynamic, shifting, restless. It stretches outward, carrying everything with it, while its contents burn, fade, and scatter. What lies beyond our horizon today may one day slip permanently out of reach. In this sense, Without end refers not to stillness but to ceaseless transformation. This brings us to the tension between what we can know and what we can only imagine. The observable universe gives us a sphere about 93 billion light-years across. That is the part we can measure, map, and test with instruments. Whether it is part of an infinite expanse or a finite but unbounded whole remains uncertain. The evidence leans toward infinity, but our sample is limited. Beyond the horizon lies the unknown. We can infer but not confirm. The unobservable remains out of reach, leaving us with probabilities rather than certainties. For many people, this is unsatisfying. We like definite answers. Is it infinite or finite? Yes or no? But the universe does not conform to our preferences. It offers us data, and from that data we build models. Those models can suggest but rarely prove, especially on the larger scales. We must learn to live with uncertainty, to accept that some questions may never be resolved. That does not mean they are not worth asking. On the contrary, the very act of asking stretches our minds and deepens our sense of place. There is also an emotional side to the idea of a universe without end. Infinity can feel overwhelming. To think that space stretches endlessly in all directions can make a person feel small, almost insignificant. But it can also be comforting. It means that the universe is larger than any of our problems, larger than any of our fears. It means that life, though fragile, is part of something vast beyond measure. Whether finite or infinite, bounded or unbounded, the universe reminds us that we are participants in a reality far greater than ourselves. One way to make peace with this is to shift perspective. Instead of asking where the universe ends, ask how far our curiosity can reach. In practice, the observable universe defines our boundary. That is the canvas on which we paint our understanding. Beyond it lies speculation, some of it grounded in theory, some of it purely imaginative. The line between observable and unobservable is not a disappointment, but a challenge. It tells us that there is always more to wonder about, always more to consider. In this sense, the universe without end is less about space itself, and more about the endlessness of inquiry. When you look at the night sky, you're seeing only a tiny slice of this. The stars visible to the naked eye are all within our galaxy. The Milky Way itself is only one of hundreds of billions of galaxies within the observable universe. Beyond that lies either infinity or something so vast it might as well be. Either way, the sky overhead is only the beginning. Every point of light is a clue, a fragment, a signpost toward the larger truth. That truth, whether infinite or finite, is beyond our direct grasp, but not beyond our imagination. So, is the universe without end? The most honest answer is that we do not know. It could be infinite, stretching forever in all directions. It could be finite but unbounded, looping back on itself. It could even be part of a larger multiverse, with countless other regions disconnected from ours. Each possibility has evidence and reasoning behind it. None can be proven absolutely. What we can say is that the universe, whatever its true shape and size, gives no indication of ending in the way a road or a wall does. It offers horizons, not edges. It offers vastness, not borders. Whether infinite or finite, it refuses to be confined by simple categories. When we ask about the shape of everything, we are really asking what kind of space we live in. Not the shape of galaxies or clusters, not the outlines of stars or planets, but the form of the universe itself. It's a question that feels abstract at first, because we are not used to thinking of space as having a shape. Space feels like a background, an emptiness in which matter sits. Yet the truth revealed by modern physics is that space is dynamic. It bends, it stretches, it curves, and it can even determine how matter moves. The shape of everything is not just a philosophical idea, it is a measurable property of the cosmos. The first clue came from Einstein's theory of general relativity. In this view, gravity is not a force pulling objects together, but the result of mass-bending space and time. A star warps the fabric around it, and planets move along the curves. This is why Earth orbits the Sun, not because of a mysterious pull, but because the Sun's mass shapes space in such a way that Earth's natural path is an orbit. Extend this idea to the whole universe, and it suggests that the distribution of all matter and energy together determines the shape of cosmic space. On large scales, there are three main possibilities. The universe could be open, closed, or flat. An open universe would have negative curvature, like a saddle. A closed universe would have positive curvature, like the surface of a sphere. A flat universe would have zero curvature, like a sheet of paper extending endlessly. Each shape implies a different geometry, a different destiny, and a different way of imagining the whole. For many years, scientists debated which shape was correct. Observations alone were not enough to settle the question. Galaxies are scattered in ways that make it difficult to measure curvature directly. But then came the discovery of the cosmic microwave background, the faint glow left over from the Big Bang. By mapping its tiny fluctuations, scientists could test the geometry of space. The results showed that the universe is flat to within a very small margin of error. Not perfectly flat, because no measurement is infinitely precise, but close enough that if there is curvature, it must be very slight. A flat universe is consistent with infinite extent, though it could also be finite if wrapped in certain ways. Imagine a video game world that looks flat but loops around on itself when you walk far enough. Space could work like that, appearing flat locally but curving globally. If this is the case, then the shape of everything is more subtle than simple labels suggest. It could be flat in our observations, but still finite in a larger sense. To test this, scientists look for repeating patterns. If light travelled around a finite, curved universe, we might see the same galaxies in different places, their light circling back. We might also see patterns in the microwave background repeating. So far, no such patterns have been confirmed. This leans toward the conclusion that space is either infinite or so large that its curvature is undetectable to us. For all practical purposes, it appears flat. But the idea of curvature remains important. Even a nearly flat universe may have local warps created by matter. Massive clusters bend light through gravitational lensing, creating arcs and rings in telescope images. These local distortions are reminders that space is not a static canvas. It is flexible, shaped by the contents it holds. On the grandest scales, the shape of everything is determined by the balance of matter, energy, and dark energy. Together, these decide whether space curves inward, outward, or not at all. It is worth pausing to reflect on how strange it is that space can bend. In daily life, space feels like nothing. You can walk across a room without thinking about the geometry of the emptiness between the walls. Yet when enough mass is involved, that emptiness itself changes. Light bends, time slows, paths curve. The idea that nothing has shape and that the shape can change is one of the most profound shifts in human understanding. It means that the universe is not a stage on which events play out, but an actor in the drama. Another possibility is that the shape of everything is more complex than simple curvature. Some theories suggest that space could be multi-connected, meaning it wraps back on itself in unusual ways. Imagine a video game where walking off one side of the screen makes you reappear on the other, or picture a hall of mirrors where images repeat endlessly. If space were multi-connected, light could travel paths that make the universe appear larger than it is, with repeated structures scattered across the sky. Searching for these signatures is part of cosmology's ongoing effort to map the true shape. There are also ideas from higher dimensional theories. In string theory, for example, our universe may be a three-dimensional surface embedded in a higher dimensional space. The shape of everything, in this view, is not limited to what we can directly observe. It could include dimensions curled up so small they are invisible, or vast structures extending beyond our perception. These ideas remain speculative, but they remind us that our concept of shape may be too limited. The true geometry could be stranger than we can imagine. The shape of everything is not just about space. Time is part of the geometry as well. In relativity, space and time form a single fabric, space-time. That means the shape of everything includes not only where things are, but how events unfold. The expansion of the universe is part of its geometry. The acceleration driven by dark energy is part of its geometry. The horizon that separates observable from unobservable is part of its geometry. Shape is not static. It evolves with time, influenced by energy and matter. Consider how this affects the ultimate question of whether the universe has an end. If space is flat and infinite, then it continues forever. If it is closed, then it loops back on itself, finite but without boundaries. If it is open, then it extends endlessly but with a different geometry. Each option carries implications for the future. In a closed universe, expansion could one day reverse. In an open or flat universe, the expansion continues indefinitely. The shape determines the destiny. Yet the evidence so far points to flatness with acceleration, suggesting a future where expansion never ends. The shape of everything, then, is one of endless outward stretching. Galaxies grow farther apart, horizons expand, and structures dissolve. Over eons, the shape evolves, not toward collapse, but toward emptiness. This is not a final answer, because new discoveries could change our understanding. But it is the picture that best fits the data we have. From a human perspective, the question of shape might seem abstract. Why does it matter if the universe is flat or curved, infinite or finite? But the answer is that it shapes everything else we know. The geometry of space influences the formation of galaxies, the paths of light, the fate of stars. It is the backdrop against which all history unfolds. To know the shape of everything is to know the stage on which we live. Even if that stage is larger than we can ever see, its form matters. There is also something deeply satisfying in the fact that we can even ask this question. For most of history, the shape of the cosmos was a matter of myth. Some cultures imagined a dome overhead. Others pictured the heavens as layered spheres. Today, through careful observation and mathematics, we can speak not only of stars and galaxies, but of the geometry of the whole. We can measure curvature, test models, and refine our understanding. It does not give us certainty, but it gives us clarity. The shape of everything is no longer guesswork. It is science, even if incomplete. When you stand beneath the night sky and look upward, you are looking into this geometry. The stars are not scattered randomly, but arranged along paths carved by space itself. The light you see has travelled those paths, bent and stretched by the curvature of everything. You may not feel the shape directly, but it surrounds you. It defines how far you can see, how galaxies cluster, how time itself flows. You are part of that shape, a point within its vast structure. To wonder about it is to recognize that you are embedded in something larger, something that gives form to existence itself. And so, when we speak of the shape of everything, we're not only describing space in mathematical terms, we're acknowledging that the universe has a form, a geometry, a structure that can be studied, mapped, and slowly understood. It may be flat, it may be curved, it may be stranger still, but whatever it is real, and it holds all of us within it. When we think about space, our instinct is to picture it as flat and empty, a stage where objects float and move. Everyday experience trains us to believe that straight lines are truly straight, that distances are fixed, that directions never change. But on cosmic scales, this is not true. Space itself can curve, bending under the weight of matter and energy. Curved space is not a metaphor. It is a measurable reality, confirmed by countless observations. And once you accept that space can bend, it opens the possibility of hidden destinations. places that appear unreachable in flat thinking, but become possible in a curved universe. The story begins with Einstein's insight that gravity is geometry. Instead of a force pulling objects across distance, mass and energy change the shape of the fabric of space-time. Picture a heavy ball placed on a stretched sheet. The sheet dips around it, and smaller objects roll toward the ball, not because the ball exerts a mysterious pull, but because the sheet itself curves. In space, stars and planets warp the geometry around them. The Earth moves along the curves shaped by the Sun, and moons follow paths shaped by their planets. This curvature does more than guide orbits, it bends light itself. When a photon passes near a massive object, its path curves. This was confirmed during a solar eclipse in 1919, when starlight passing near the Sun was observed to shift, proving Einstein's theory. Since then, gravitational lensing has become a powerful tool in astronomy. Galaxies and clusters act as cosmic lenses, magnifying and distorting the light of even more distant galaxies behind them. This allows us to see objects otherwise too faint to detect. Hidden destinations become visible only because curved space brings their light to us. On larger scales, curved space raises even stranger possibilities. If space itself curves back on itself, then travelling in a straight line could eventually return you to your starting point. This is difficult to imagine because we're used to flat surfaces. But think again of the Earth. Walk in one direction long enough and you circle back. To someone who believed the Earth was flat, this would seem impossible, yet curvature makes it real. Space could behave the same way. What appears infinite might actually loop around, hiding destinations that are closer than they seem in straight-line thinking. Some models of the universe suggest that space could be finite but unbounded in exactly this way. If true, then beyond the observable horizon lies not endless space, but a return. Galaxies we see in one direction could, in principle, be the same galaxies seen again from another, their light looping around curved space. Scientists have searched for these repeated patterns, looking in the cosmic microwave background for identical patches, but so far none have been confirmed. That does not rule it out. It only means that if space is curved in this way, the scale is much larger than the part we can see. Curved space also shapes what we mean by hidden destinations. Black holes are the most dramatic example. Their mass is so concentrated that space curves steeply inward. At a certain distance, called the event horizon, the curve becomes so deep that not even light can escape. To an outside observer, the black hole appears as a dark sphere, with no signals coming from within. But the inside is not nothing. It is a hidden region of space and time, cut off from the outside by extreme curvature. To enter is to cross a boundary beyond which return is impossible. This is perhaps the most literal example of a hidden destination created by curved space. Wormholes are another theoretical possibility. In the equations of relativity, curved space can, in principle, connect distant regions through tunnels, shortcuts linking far apart destinations. These wormholes are solutions to the math, though whether they exist in reality is unknown. If they did, they would represent the ultimate hidden destinations, doors through curved space that bypass the long journey across flat distances. So far, no evidence for wormholes has been found, but the possibility remains an active area of thought. Even if they do not exist naturally, the idea that curvature could fold space to create connections shows how flexible the universe might be. On less exotic scales, curved space still hides destinations in subtler ways. Gravitational lensing can create multiple images of the same object, tricking us into thinking we are seeing two galaxies when in fact it is one seen along different curved paths. Without careful study we would not realize they are the same. Space, bent by intervening mass, disguises the truth. What appears as separate destinations are in fact one. Light itself becomes a traveller guided by the geometry, showing us a universe that is less straightforward than it seems. This also has implications for the question of what lies beyond. If space curves globally, then the other side of the universe may not be other at all, but simply another route back to here. The unseen may be the familiar, repeated in ways we cannot yet detect. Curvature transforms our concept of beyond, turning it into something less like an edge and more like a fold. What is hidden is not necessarily elsewhere. It may be a distorted reflection, brought into view by the geometry itself. There is also the matter of expansion. As space stretches, curvature evolves. In the early universe, inflation may have smoothed space into near flatness, but small deviations could remain. Over time, dark energy shapes how curvature develops, flattening on large scales, while local structures like galaxies curve space intensely. This dynamic interplay means that hidden destinations are not fixed. They emerge and shift as the geometry evolves. A galaxy visible now may become hidden later as expansion pulls it across the horizon. A black hole forming from a dying star creates a new hidden region where none existed before. Curved space is not static. It creates and erases hidden destinations over time. From a human perspective, the idea of curved space is difficult because it is so unlike ordinary experience. We walk on floors, drive on roads, fly through air, all of which feel flat. Even the curvature of the Earth is not obvious without long journeys. To accept that the very fabric of space can bend is to accept that the background of existence is not rigid. It is flexible, malleable, responsive to matter and energy. Once you accept this, the universe becomes stranger and richer. The possibility of hidden destinations follows naturally. Some philosophers have argued that hidden destinations in curved space reflect the limits of knowledge itself. There are regions we cannot see, not because they do not exist, but because space itself conceals them. In this sense, curved space mirrors the boundaries of our perception. Just as our eyes cannot see ultraviolet light without tools, our senses cannot detect the full shape of space without instruments. Even with instruments, some destinations remain hidden, not for lack of effort, but because the universe itself prevents access. It is worth noting that curved space does not always hide. Sometimes it reveals. Without gravitational lensing, we would not be able to see some of the earliest galaxies. Their light would be too faint, too thinly spread. But curved space magnifies them, bending and focusing the light so that it reaches us. In this way, curvature acts like a natural telescope, showing us what would otherwise remain invisible. The universe both hides and reveals, depending on how its geometry bends. As you lie back and imagine this, it is helpful to think of curved space not as a puzzle to solve, but as a landscape to explore. Just as mountains and valleys shape the paths of rivers and travellers, curves in space shape the paths of light and matter. Hidden destinations are like valleys obscured from view until you climb the ridge. They are there, waiting, shaped by the geometry itself. The universe is not flatland but terrain, uneven and full of surprises. To move through it is to discover not just distance but form. And while much of this is theoretical, much of it is also measurable. Astronomers map gravitational lensing, detect arcs of light, and use them to infer the presence of unseen mass. They track the shapes of galaxies and clusters, reading the story of curvature written across the sky. They test models of global geometry by measuring the microwave background. The science is slow, precise and careful, but behind it lies a simple truth. Space is not empty. It has shape, and that shape hides and reveals destinations in ways that challenge our intuition. So when we ask what lies on the other side of the universe, curved space gives one answer. It may not be another place in the way we imagine. It may be a hidden reflection, a distant galaxy seen along a bent path, or even a return to our own region through a loop of geometry. The other side may be closer than we think, folded into the shape of everything. Curved space ensures that the universe is not straightforward. It ensures that mystery remains, not because of a lack of effort, but because the fabric itself is more complex than a simple flat plane. Hidden destinations are built into the geometry, reminders that the universe is larger, stranger, and more fascinating than the straight lines of daily life suggest. When people ask what might lie beyond the universe, one of the most intriguing answers science has proposed is the idea of a multiverse. The word itself suggests many universes, not just one, and it changes the scale of the question entirely. Instead of asking whether our universe has an edge or an end, we begin to ask whether it is only one bubble among countless others. If so, then the other side of the universe may not be more of the same space we see stretching outward. It may be something entirely disconnected, another universe with its own rules, its own history, perhaps even its own dimensions of space and time. The multiverse is not a single idea, but a family of hypotheses. Each comes from a different branch of science, from cosmology to quantum mechanics to string theory. They share the same basic suggestion, that what we call the universe might not be the whole of reality, only a part of it. And if that is true, then the other side of the universe is not a distant galaxy or a hidden region of curved space. It is a doorway into something beyond our comprehension. One of the first hints of a multiverse comes from inflation theory. According to this idea, in the earliest fraction of a second after the Big Bang, the universe expanded at a rate faster than light, ballooning outward by unimaginable factors in less than the blink of an eye. Inflation explains why the universe today looks so uniform on large scales. Without it, distant regions would never have been in contact to even out their properties. But inflation also suggests that the expansion may not have happened everywhere at once. In some models, inflation continues eternally in different regions, producing endless bubbles of space-time. Each bubble could form its own universe, with its own laws of physics. Our observable universe would be one bubble among countless others, floating in an infinite multiverse. This picture is sometimes called eternal inflation. In it, new universes are constantly forming, sprouting like buds on a vast tree. Each one expands and evolves independently. Some may grow to look like ours, filled with galaxies and stars. Others may have very different properties, perhaps no stable matter at all, perhaps dimensions curled in ways that prevent complexity. From this perspective, the universe we see is not the whole, but one bubble in an endless froth. The other side of our universe might not even connect to these others. They are separated by inflating space, unreachable, forever apart, and yet they exist in the same larger reality. Another version of the multiverse comes from quantum mechanics. In quantum theory, particles exist in multiple possible states until observed. This leads to the famous thought experiment of Schrödinger's cat, which is both alive and dead until someone opens the box. One interpretation of this behaviour is the many-worlds hypothesis. In it, every possible outcome of a quantum event actually happens, but in different branches of reality. When you flip a coin, one universe exists where it lands heads, and another where it lands tails. Every decision, every random event creates a branching of worlds. If this is true, then there are countless universes layered alongside ours, each as real as the one you experience, each containing versions of you living different lives. In this view, the other side of the universe is not distant in space, but adjacent in possibility. It is not a faraway galaxy, but a nearby reality you can never cross into. The multiverse of quantum mechanics is infinite in a different sense. It does not stretch endlessly outward, but endlessly sideways into every possible branch of history. This idea remains speculative, but it is consistent with the mathematics of quantum theory. Whether it reflects actual reality is still debated, but it shows how deeply the multiverse concept reaches. String theory offers another path. In this framework, the basic building blocks of reality are not particles, but tiny vibrating strings. The vibrations of these strings determine the properties of matter and energy. But for string theory to work mathematically, extra dimensions are required, beyond the three of space and one of time we experience. These extra dimensions may be compact and hidden, curled up so small we cannot detect them. In some versions, different universes arise from different configurations of these dimensions. The landscape of possible universes is vast, with each one defined by a different arrangement of physical laws. Our universe is simply one of many valleys in this landscape. Others exist, governed by laws so different that we might not even recognize them as universes. From this point of view, the multiverse is not just a set of possibilities, but a natural outcome of fundamental physics. If the mathematics allows many different solutions, and if inflation or other processes can realize them, then the multiverse follows. It is not an optional speculation, but an unavoidable consequence. Whether this is true remains uncertain, but it underscores how serious the idea has become in theoretical science. Of course, the multiverse raises difficult questions. The most obvious is whether it can ever be tested. If other universes are disconnected from ours, forever beyond observation, how can we know they exist? Some suggest that collisions between bubble universes could leave imprints in the cosmic microwave background. Others argue that the fine-tuning of physical constants in our universe is indirect evidence. For example, the values of forces and masses in physics seem precisely adjusted to allow stars, chemistry, and life. In a single universe, this looks like an extraordinary coincidence, but in a multiverse, where countless universes exist with different constants, it is not surprising that one of them would allow life. We live in that one simply because we can. This line of reasoning is called the anthropic principle. It is controversial because it risks sounding circular. Of course, we find ourselves in a universe that permits us, yet it becomes more compelling when combined with the multiverse. Instead of asking why the universe is so finely tuned, we consider that there may be countless universes with different settings, and ours is simply one that works. The other side of the universe, in this sense, could be a place where the laws are shifted slightly, where stars never form, or where atoms never bind. These universes are unobservable, but their possibility explains the strangeness of our own. Some thinkers go further and imagine multiverses of even broader scope. There are ideas of mathematical universes, where every consistent mathematical structure exists as a reality. In that framework, any possible arrangement of laws and matter is realized somewhere. Our universe is one such structure, but others exist, equally real. In such a vision, the multiverse is not just large, it is everything, every possibility, every pattern. The other side of the universe is not a location, but an alternative, a different expression of reality. Critics of the multiverse argue that it is untestable, and therefore not science. They point out that if no observation can ever distinguish between universes, then the hypothesis is more philosophy than physics. Defenders respond that the multiverse is a prediction of theories we can test in other ways. If inflation or string theory prove accurate in areas we can observe, then their multiverse implications follow. In this way, the idea becomes indirectly testable. The debate continues, reminding us that science often works at the edge of what can be known. For people outside physics, the multiverse carries a different kind of fascination. It suggests that reality is far larger and stranger than we experience. It allows for the possibility of endless variation, endless worlds, endless versions of ourselves. Whether or not these things exist, the idea stretches the imagination. It turns the question of the other side of the universe into something broader, not just what lies beyond, but what else could exist entirely outside our horizon, in realms we will never touch. And while the multiverse remains speculative, it serves an important role. It reminds us that our universe, vast as it is, may not be the whole story. It humbles us by showing that even our best theories point to possibilities we cannot directly confirm. It inspires us to keep asking, to keep building, to keep imagining. The multiverse may or may not exist, but the fact that science takes it seriously shows how much larger the cosmos might be than we ever guessed. So when we ask what is on the other side of the universe, the multiverse gives one answer. Perhaps the other side is not more of the same, but something entirely different. Perhaps it is another universe with different laws, a bubble born from inflation, a branch of quantum possibility, or a valley in the string landscape. Perhaps the other side is not even reachable in principle, only imaginable, and yet in imagining it, we take one more step toward grasping the scale of reality, a scale so vast that our universe itself may be only one of countless worlds. When people first hear the phrase parallel realities, it often sounds like something taken from science fiction, the kind of idea reserved for stories where characters slip between worlds or encounter alternate versions of themselves. But in modern science, parallel realities are not just the domain of imagination. They emerge naturally from theories that try to explain how the universe works on its deepest levels, and when paired with the concept of bubble universes, they paint a picture of reality that is far larger, far stranger, and far more complex than anything we can touch directly. To begin with, think about the notion of parallel realities in quantum mechanics. At the quantum level, particles exist in states of uncertainty. An electron does not have a definite position until it is measured. Instead, it exists as a wave of possibilities. One interpretation of this, called the many worlds interpretation, suggests that every possibility is realized. When a quantum event occurs, the universe branches. In one branch, the particle is here. In another, it is there. Every possible outcome unfolds in its own branch, creating parallel realities. From our point of view, we only ever experience one branch, but the others continue, just as real, just as complete. If this interpretation is correct, then parallel realities are not hypothetical but inevitable. Each moment, every particle interaction splits the universe into new branches. Somewhere, there is a version of you who made a different choice this morning, who lives in a slightly different world shaped by that choice. Somewhere else, there are versions so different they are unrecognizable, shaped by events diverging millions of years ago. These realities are not connected in space but in possibility. They exist alongside ours, parallel in the structure of quantum mechanics. Bubble universes, on the other hand, emerge from inflation theory and cosmology. In this framework, the rapid expansion that shaped our universe after the Big Bang may not have been unique. Inflation could occur in different regions of the larger space-time, creating bubbles of universes. Each bubble would expand, cool, and form galaxies and stars, but each might have different physical properties depending on the conditions at its birth. Our observable universe is one such bubble, vast and full, but not necessarily alone. Countless others could exist, separated by regions of space that continue to inflate, forever keeping them apart. When you put these two ideas side by side, the picture becomes staggering. Parallel reality suggests branching universes born from quantum events. Bubble universes suggest separate universes born from cosmic inflation. Together, they hint at layers of multiplicity. Not only might there be countless universes beyond our own bubble, but within each bubble there may be countless branching realities. If so, the total number of universes is not just vast, it is beyond calculation. A structure of reality so immense that our single observable universe is a fraction of a fraction. From a scientific perspective, these ideas arise naturally, not from wishful thinking. Inflation explains the uniformity of the cosmos and the distribution of galaxies. Quantum mechanics explains the behavior of particles and the success of modern physics. Neither was invented to propose parallel worlds or bubble universes. Those conclusions follow as natural consequences when the theories are taken seriously. This is part of what makes them so powerful. They are not just stories, they are possibilities written into the mathematics. Still, it is natural to ask whether parallel realities or bubble universes can ever be detected. With parallel realities, the challenge is that they do not interact with one another. Once a branch splits, it evolves independently. There is no known way to move from one to another, no way to send signals across. They are parallel in the strictest sense, adjacent but disconnected. This makes them scientifically elusive. They explain quantum phenomena without contradicting observation, but they cannot easily be tested. Bubble universes face a similar issue, though with slightly more room for evidence. If two bubbles collided in the distant past, their impact might leave traces. Some scientists suggest that circular patterns in the cosmic microwave background could be scars of such collisions. Searches have been conducted, but so far no definitive evidence has been found. Another indirect clue is the fine-tuning of physical constants. The values of fundamental forces in our universe seem remarkably suited to forming stars and life. In a multiverse of bubble universes, this fine-tuning is less surprising. With enough universes, one will naturally have the right values. We happen to live in that one because it permits us. This reasoning is not proof, but it makes the bubble hypothesis appealing. Beyond evidence, there is also a philosophical question. If parallel realities and bubble universes exist but are forever beyond our reach, are they meaningful? Some argue yes, because they follow from our best theories and help explain puzzles. Others argue no, because untestable ideas lie outside science. This debate continues, but meanwhile the concepts inspire deeper thought about what reality might be. They expand our imagination, stretching our understanding of what the universe could mean. It is also worth noting that these ideas are not mutually exclusive. Our universe could be a bubble within inflationary space, and within it, quantum mechanics could produce branching realities. Each bubble could contain its own multiverse of possibilities, layered within the greater multiverse of bubbles. Reality in this picture is not just one universe or even many universes. It is a hierarchy of worlds, nested and layered, expanding in every direction of possibility. To imagine this is to confront the limits of language. We are used to words like universe, meaning everything. To say there are many universes feels contradictory, but if reality is larger than our universe, then the word must stretch. Universe becomes one bubble among many, one branch among countless, one thread in a fabric beyond measure. The other side of our universe is not just more space, it is more universes, disconnected yet real. These ideas also raise questions about identity. If parallel realities exist, then there are countless versions of you, each making different choices, each living a different path. If bubble universes exist, then there may be versions of you shaped by entirely different physics, perhaps unrecognizable. Does this diminish the importance of your life here? Or does it enrich it, showing that existence is more varied than you can imagine? Philosophers and scientists alike wrestle with these questions, because the implications are as personal as they are cosmic. For all their strangeness, parallel realities and bubble universes share a common theme. They remind us that what we see is not necessarily all there is. The observable universe, vast as it is, may be only one island. Beyond it lie other islands, some near impossibility, some far in inflationary space. We may never visit them, but they reshape how we think about our place. Instead of being everything, our universe becomes one part of something larger, a participant in a reality without obvious limits. And while evidence remains uncertain, the act of exploring these ideas is valuable in itself. It pushes science to the edges of knowledge, testing what can be said, what can be measured, what can be imagined responsibly. It forces us to refine our theories, to ask whether they describe just what we see or more than we can see. Even if parallel realities and bubble universes remain unconfirmed, the effort to understand them deepens our grasp of the universe we do inhabit. When we wonder about the other side of the universe, parallel realities and bubble universes offer one of the most expansive answers. The other side may not be across a distance, but across a possibility. It may not be galaxies and stars, but entire worlds branching or bubbling beyond our reach. The cosmos may be larger not only in space but in number, a collection of realities where ours is one among countless others. When people imagine the universe, one of the first questions they often ask is, where does it end? It feels natural to think in those terms because almost everything we know has edges. A book has a last page, a field has a fence, a house has walls, even the earth itself has a surface you can walk around. Our senses are trained to expect boundaries. So when we look up at the night sky, our instinct is to wonder where the edge of it lies, as if we could someday arrive there and see what is beyond. But the strange thing about the universe is that the edges we imagine may be illusions. The first way this illusion shows itself is in the horizon of the observable universe. We see a boundary at about 46 billion light-years in every direction. But that boundary is not the edge of reality. It is simply the farthest distance light has had time to travel since the Big Bang. Beyond it, the universe continues. We cannot see it, but it is there. The horizon looks like an edge, but it is not. It is a limit of vision, not of existence. Just as the horizon on Earth is not the end of the planet, but the limit of what your eyes can reach. The cosmic horizon only marks what is visible from our position in space and time. Another kind of edge illusion comes from our instinct to picture space as flat. In daily life, when you walk in a straight line, you expect to go farther away. But if space is curved, then going straight might eventually bring you back to your starting point. The surface of Earth is the simplest analogy. To someone standing on the ground, the horizon looks like an edge. Walk toward it, and it moves with you. Sail across the ocean, and the horizon never arrives. Instead, you eventually circle back around the planet. From this perspective, the Earth has no edges, only curvature. Space itself may work in the same way. What feels like an edge could just be the limit of our perception, a mirage created by geometry. Even black holes present a similar trick. To an outside observer, the event horizon looks like a sharp edge. Matter falls in and seems to vanish, never returning. But the event horizon is not a solid surface. It is a region of curved space where escape becomes impossible. There is no wall, no physical barrier, only a limit shaped by gravity. The edge is an illusion of perspective, a horizon created by the way light and time behave. The inside of a black hole remains hidden, not because there is nothing there, but because space itself bends so steeply that no signals can escape. What we call an edge is simply a place where information is cut off. The illusion of edges also appears in how we think about beginnings and endings. The Big Bang is often described as the beginning of everything, a singular edge in time. But physicists are careful to point out that the Big Bang may not have been a single point where everything started. Instead, it could be the moment when the universe became hot and dense, the earliest phase we can describe with current theories. Beyond that, we do not yet know. There could have been something before, some larger framework from which our universe emerged. The edge in time that we call the beginning may be no more absolute than the edge in space that we call the horizon. Both are limits of knowledge, not necessarily limits of reality. This distinction matters because it changes how we think about the question of the other side. If we insist on seeing edges everywhere, we imagine the universe as a container with walls. Beyond the walls lies nothing, or something unknown. But if the edges are illusions, then the universe is not a container at all. It is a continuous fabric with horizons, curves, and limits of observation. The other side of the universe is not outside a box. It is simply beyond our reach, either because light has not had time to get here, or because geometry hides it from view. Astronomers sometimes describe the observable universe as a sphere centered on us, but this too can create the wrong impression. It makes it sound as though we are in the middle with edges all around. In reality, every observer anywhere in the universe would see the same. Their observable universe would also appear as a sphere centered on them. Each sphere overlaps with others, and together they cover the whole. There is no privileged center, no real boundary. The edges are illusions born from perspective. Another way to think about this is through the expansion of space. Because space itself stretches, galaxies appear to move away from us in every direction. The farther they are, the faster they recede. At some distance they recede faster than light can travel, and so their signals never reach us. This creates another apparent edge, the limit of observability. But again, it is not a wall. The galaxies are still there, moving through their own regions of space. The edge is only a result of physics limiting what can reach us. From their perspective, they are at the centre of their own sphere, and we would be beyond their horizon. Each observer sees edges, but none are real in the sense of stopping points. This is why cosmologists caution against thinking of the universe like a room with walls. It is more accurate to think of it as a vast landscape hidden by fog. The fog is not a boundary. It is a limit of sight. Beyond it, the landscape continues whether you can see it or not. The illusion of edges comes from mistaking the horizon for a wall. The truth is that horizons shift as you move, change as you wait, and expand as time goes on. Edges in the universe are never fixed. They are always relative, always shaped by perspective and the limits of information. There is also the question of what happens in the very distant future. Because of accelerated expansion, more and more galaxies will eventually move beyond our horizon. To future observers, the universe will look smaller and emptier, as though it has an edge closer than ours. They will see only the galaxies bound to their local group. The illusion of edges will grow stronger for them, not because the universe has shrunk, but because their horizon has receded. Edges, in this sense, are not features of reality, but experiences of observers. They shift with time, change with expansion, and differ depending on where you stand. The illusion of edges has deep philosophical implications. It shows that many of our instincts about reality are shaped by the small scales we live on. We're used to rooms, fields, surfaces, and objects, all with borders. We project that intuition onto the cosmos and expect the same. But the universe does not follow those rules. It is governed by relativity, expansion, and quantum mechanics. Its edges dissolve under scrutiny, replaced by horizons and curves. The universe teaches us that what looks like a boundary may simply be the edge of vision, the end of information, or a trick of geometry. For science, this is not disappointment. It is an invitation. Illusions of edges challenge us to refine our models, to build instruments that see farther, to question assumptions. They remind us that reality is not limited to what appears obvious. The horizon once seemed like an edge of the world, until explorers crossed oceans and proved otherwise. The edge of the Milky Way once seemed like the edge of everything, until telescopes revealed galaxies beyond. Each time, what looked like an edge turned out to be an illusion. The pattern suggests that even now, what we see as the limit of the universe is likely another mirage, another boundary waiting to dissolve with deeper understanding. From a personal perspective, the illusion of edges can be strangely comforting. It means that the universe is not boxed in. It means that reality does not end abruptly at a wall of nothing. It means that there is always more beyond, whether or not we can see it. This endlessness, whether infinite or simply beyond reach, keeps curiosity alive. It keeps questions open. It prevents finality, leaving room for wonder. The illusion of edges is not a flaw. It is part of what makes the universe vast and mysterious. So when you picture the other side of the universe, it helps to set aside the image of walls or borders. Instead, imagine horizons that move as you move, limits that shift as time passes, boundaries that are not fixed but relative. The universe has no edge in the sense of an ending. What we see as edges are illusions created by light, time, and perspective. Beyond them, reality continues, larger than we can imagine, waiting silently beyond the reach of our instruments. Long before telescopes, long before theories of relativity and quantum mechanics, human beings looked at the night sky and wondered what lay beyond it. The stars were always there, scattered across the darkness, shifting slowly with the seasons. For early people, they were not distant suns, but lights fixed in the heavens, mysterious points whose purpose invited interpretation. Every culture, in its own way, imagined what the stars meant and what existed past them. These stories, passed down through myth, legend and ritual, shaped the way entire civilizations understood the cosmos. They may not have been scientific in the modern sense, but they carried their own kind of truth. They reveal how humans, faced with mystery, always search for meaning. In Mesopotamia, some of the earliest known astronomers carefully recorded the motions of the stars and planets. To them, the heavens were not empty space, but the dwelling places of gods. The stars themselves were divine symbols, arranged as part of a great order. Beyond them lay the realms of the gods, places inaccessible to mortals. The night sky was a map of divine will, a canvas on which celestial beings wrote their messages. Astrology, born in this era, was a way of reading those messages, interpreting what the stars beyond Earth's sky foretold. For the people who lived in these river valleys thousands of years ago, the other side of the universe was divine territory, a domain of higher powers. In Egypt, the stars also carried sacred significance. The gods were linked to constellations, and the movements of the heavens guided the construction of temples and pyramids. The Milky Way was seen as a celestial river, a mirror of the Nile flowing across the sky. Beyond the stars lay the afterlife, a place where souls travelled after death. The pharaohs in particular were thought to ascend to the stars, becoming one with the gods. The other side of the universe for the Egyptians was both a journey and a destination, the eternal home of divine and royal spirits. In ancient Greece, philosophers debated what lay beyond the stars with remarkable curiosity. Some, like Aristotle, imagined the universe as a set of crystalline spheres. The stars were embedded in the outermost sphere, and beyond that sphere was the unmoved mover, a divine principle that caused motion without itself moving. For him, the universe had an edge, a physical boundary, and beyond it was the realm of pure perfection. Others, like Democritus, speculated about infinite worlds beyond our own, made of atoms moving through the void. For him, the universe had no edge, only endless repetition. Between these views lay a tension that still exists today, the pull between a finite cosmos with boundaries and an infinite one without end. The Romans inherited many of these Greek ideas, but they also wove them into their mythology. The gods lived among the stars, influencing the fates of mortals. The constellations themselves were stories, heroes and creatures placed in the heavens as eternal reminders. To look beyond the stars was to look into the realm of gods and fate, a place both inspiring and intimidating. The other side of the universe was not empty for them. It was filled with divine presence. Far to the east in India, ancient texts like the Rig Veda described a cosmos of cycles. The universe was not a single creation, but an endless series of expansions and contractions, births and destructions. The stars were part of this grand rhythm, lights in a cosmic dance without beginning or end. Beyond them lay higher realms of existence, places where gods dwelled and souls travelled through reincarnation. The other side of the universe was not a final destination, but a step in an eternal cycle, a passage between lives and realities. In China, the heavens were deeply tied to order and harmony. The emperor was seen as the son of heaven, ruling under the mandate of cosmic balance. The stars reflected this balance, their patterns marking the seasons and guiding rituals. Beyond the stars lay the realm of heaven itself, a place of ancestors and divine forces. To maintain harmony on Earth was to align with the order beyond. The other side of the universe was not chaos or emptiness, but structure, hierarchy and cosmic authority. In the traditions of indigenous peoples across the world, the stars often played central roles in stories of creation and guidance. For many Native American cultures, the stars were ancestors, spirits, or guides. The Lakota, for instance, told stories of the Star People, beings connected to humanity who lived beyond the visible sky. The Navajo saw the stars as part of their sacred stories of order and balance. For the Maya, the heavens were a great calendar, cycles of time written in light. Beyond the stars lay the realms of gods and ancestors, places that were not abstract but woven directly into daily life. In the Pacific Islands, navigators used the stars to cross vast oceans. For them, the heavens were maps, and beyond the stars lay destinations on Earth, as well as spiritual homelands. The other side of the universe was both practical and mystical, a guide for voyages of survival and a connection to realms of gods. The stars were bridges, and to move beyond them was to move into sacred space. In the myths of Northern Europe, the stars were woven into great cosmic structures. The Norse spoke of Yggdrasil, the world tree that connected the realms of gods, humans, and giants. The stars hung in its branches, lights marking the pathways between worlds. Beyond them lay Asgard, the home of the gods, and other realms in the cosmic order. The universe was not boundless for them, but layered, structured, with edges that were thresholds into new domains. Each threshold led not to emptiness, but to another world filled with beings and stories. Across Africa, different cultures imagine the stars as homes of spirits or ancestors. The Dogon people of Mali told stories of Sirius, describing details about its companion star long before modern astronomy confirmed them. For them, the stars carried knowledge and mystery. Beyond them lay truths hidden from ordinary vision, accessible only through myth and initiation. The other side of the universe was not absence, but depth, layers of meaning that only tradition could reveal. All these traditions, despite their diversity, share a common feature. None of them saw the stars as the end. For every culture, the heavens were a gateway. Beyond them lay gods, ancestors, cycles or structures. The stars were not edges but thresholds, places where the known world met the unknown. The idea of an empty universe, stretching endlessly without meaning, is relatively modern. For ancient peoples, the universe was always filled with spirits, with divine presence, with cycles of creation. The other side of the universe was never nothing. It was always something. This is significant because it shows how deeply human imagination resists the idea of a hard edge. When faced with the mystery of the stars, people filled the unknown with meaning. Sometimes it was gods and myths. Sometimes it was cycles and ancestors. Sometimes it was cosmic order. But always it was something more than emptiness. The illusion of edges, so powerful to us now, was not present in the same way then. They did not imagine hitting a wall of nothing. They imagined passing into another realm, another story. Even now, these ancient visions shape us. The constellations we use today carry Greek and Roman names. The zodiac signs come from Mesopotamian astrology. Our calendars echo Mayan and Chinese cycles. The stories people told about what lies beyond the stars still influence how we speak about the heavens. Even as science offers new explanations, the old myths remain in language, art and culture. They remind us that wondering about the other side of the universe is not a new question. It is one of the oldest, and perhaps that is why these stories still matter. They show that across time and space, people have always looked upward and wondered. Whether the answer was gods, ancestors, cycles, or infinite worlds, the act of asking was the same. The other side of the universe was always mysterious, always beyond reach, always a place for imagination. Today we use telescopes and equations, but the impulse is the same. We are still telling stories about what lies beyond. We are still trying to picture the unseen. When we look at the universe with our eyes, with telescopes, with instruments that can capture every wavelength of light, we might think we're seeing the whole picture. Stars fill the sky, galaxies stretch across space, and clusters form vast webs of matter. It feels like a complete view, a map of everything that exists. But in truth, what we see is only a small fraction. Most of the universe is invisible, not because it hides behind dust or distance, but because it is fundamentally different. Scientists call this invisible part dark matter and dark energy, and together they make up nearly everything. Ordinary matter, the kind that makes stars, planets and people, accounts for less than 5%. The rest is the dark unknown. Dark matter was discovered not by being seen, but by being inferred. In the 1930s, an astronomer named Fritz Zwicky studied clusters of galaxies and noticed something strange. The galaxies were moving faster than expected. According to the laws of gravity, they should have flown apart, scattered by their own motion. But they held together. The only explanation was that there was more mass than what was visible. Something unseen was providing the extra gravity needed to keep the cluster intact. Zwicky called it Dunkel Materie, dark matter. Decades later, another astronomer, Vera Rubin, confirmed the mystery on galactic scales. She measured the rotation of galaxies and found that stars at the edges moved just as fast as those near the centre. If galaxies were made only of the matter we can see, the stars on the outskirts should move more slowly, just as planets in the solar system move slower the farther they are from the sun. But they didn't. The galaxies behaved as though they were surrounded by massive, invisible halos of matter. This unseen substance was shaping their rotation, holding them together. Today, dark matter remains unseen directly, but its presence is undeniable. It reveals itself through gravity. It bends light through gravitational lensing, magnifying distant galaxies. It holds clusters together. It shapes the large-scale structure of the cosmos, guiding the formation of galaxies and filaments. Simulations of the universe without dark matter fail to produce the web-like structures we observe. Simulations with dark matter match reality. The invisible explains the visible. But what is dark matter made of? That question remains unanswered. It does not emit or absorb light, which is why it is invisible. It does not interact strongly with ordinary matter. The leading ideas suggest it could be made of new kinds of particles, perhaps weakly interacting massive particles, or WIMPs, that pass through matter almost unnoticed. Others suggest axions, hypothetical particles that could also account for the missing mass. Despite decades of searching with sensitive detectors deep underground, no direct detection has yet been confirmed. The nature of dark matter is one of the great unsolved puzzles of science. Then there is dark energy, an even stranger mystery. In the late 1990s, astronomers studying distant supernovae expected to find that the expansion of the universe was slowing down, pulled by the gravity of all its matter. Instead, they found the opposite. The expansion was speeding up. Galaxies were moving away from one another faster over time. To explain this acceleration, scientists proposed dark energy, a form of energy inherent to space itself. Unlike matter, which pulls things together, dark energy pushes them apart. Dark energy now makes up about 70% of the universe. Its exact nature is unknown. One possibility is that it is the cosmological constant, a simple energy of empty space, first proposed by Einstein and later revived. Another is that it is a dynamic field that changes over time. Whatever it is, its effects dominate the universe. It dictates the future, ensuring that expansion accelerates. Galaxies that are visible today will drift beyond our horizon, carried away by dark energy's push. In trillions of years, distant galaxies will no longer be seen at all. Dark energy will have erased them from view, not by destroying them, but by stretching space too quickly for their light to arrive. Together, dark matter and dark energy form the dark unknown, the vast majority of reality we cannot see. They shape everything, yet remain elusive. It is as if we live in a house where most of the walls are invisible. We can see the furniture and the doors, but the structure itself is hidden. We feel its presence. We rely on it, but we cannot grasp it directly. This is not a failure of science, but a reflection of how much there is still to discover. The universe is telling us that our picture is incomplete, that what we call reality is only a thin slice of the whole. The dark unknown also challenges how we think about the other side of the universe. If most of what exists is invisible, then even here, within the observable universe, we're already surrounded by the unseen. What lies beyond may not just be more galaxies and stars, but more of the dark unknown stretching endlessly. The edges we imagine are not just horizons of distance, but boundaries of knowledge. Beyond them, dark matter and dark energy continue, shaping a reality we can sense only indirectly. Scientists are pursuing the dark unknown with remarkable persistence. Experiments buried in mountains or submerged in deep mines are designed to catch rare interactions of dark matter particles. Telescopes scan the sky for subtle effects of dark energy on cosmic structures. The effort is vast, yet progress is slow, because the dark unknown is subtle. It does not give itself away easily. Each new experiment is a chance to learn, but each null result deepens the mystery. Still, the search continues because the stakes are high. To understand dark matter and dark energy is to understand most of the universe. The presence of the dark unknown also forces us to reconsider what we mean by seeing. We often equate sight with knowledge, but in cosmology, much of what we know comes not from seeing directly, but from inference. We see galaxies, but we deduce halos of dark matter. We see expansion, but we deduce dark energy. Our instruments reveal effects, not causes. We reconstruct reality from shadows. This reliance on inference may feel unsatisfying, but it is also a strength. It shows that science can uncover truths even when they are hidden, that knowledge does not depend only on direct observation. There is also a humbling aspect to this. For centuries, humans believed they had a clear view of the cosmos. We thought Earth was the centre. Then we thought the Sun was the centre. Then we learned that the Milky Way was only one galaxy among many. Now we learn that even the matter we see is only a small fraction. Each step shifts us farther from the idea of being central or complete. The dark unknown is the latest reminder that we are only beginning to understand. From another perspective, though, this is hopeful. To live in a universe where most of reality is unknown is to live in a universe full of possibilities. The dark unknown is not a dead end. It is a frontier. It means that discovery is not finished, that science still has vast horizons to explore. Dark matter and dark energy may someday be explained, and when they are, our understanding of reality will expand again, just as it has with every previous revelation. In the meantime, the dark unknown remains both unsettling and inspiring. It tells us that what we see is not the whole, that the universe is richer and stranger than we can picture. It reminds us that our place in the cosmos is small, but our capacity to wonder is large, and it shows that even in the age of advanced instruments and powerful theories, mystery remains at the heart of existence. The other side of the universe is not just about distance, it is about the dark unknown, the invisible majority that defines reality itself. When we talk about galaxies, we often think of them as bright and permanent things, collections of billions of stars drifting together through space. From the spiral arms of the Milky Way to the hazy light of Andromeda, galaxies feel like steady markers in the night sky, symbols of vastness that exist far beyond us yet remain visible. But the truth is that many galaxies already lie beyond our reach, and more will join them in time. This is not because they are destroyed, but because the fabric of space itself is stretching, carrying them farther and farther away until their light can no longer reach us. To understand this, it helps to picture the expansion of the universe. Ever since the Big Bang, space has been stretching in every direction. Galaxies are not flying through empty space like sparks scattered from a fire. Instead, they are carried outward by the growth of space itself. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart. None of the dots are special, none are at the centre, and the motion is not through the balloon, but of the balloon's surface expanding. This is how galaxies behave in the universe. They remain mostly fixed in their local groups, but the space between groups grows. On small scales, gravity holds galaxies together. The Milky Way will not be torn apart by expansion, nor will it lose its stars. In fact, our galaxy and the Andromeda Galaxy are moving toward each other, pulled together by gravity strong enough to overcome the general expansion. In several billion years, they will merge into a larger galaxy, often referred to as Milkomeda. But beyond the reach of gravity's binding power, expansion dominates. Clusters drift apart, superclusters separate, and on the largest scales, galaxies recede from one another. The key to which galaxies are within reach and which are beyond lies in the cosmic horizon. Light takes time to travel, and because space is expanding, there is a limit to how far light can reach us. Galaxies inside that horizon are visible, their light arriving after billions of years of travel. But galaxies beyond that horizon are unreachable. Even if they emit light, space expands so quickly that the light never arrives. These galaxies exist, but we will never see them. What makes this more dramatic is that the horizon is not fixed. As dark energy drives accelerated expansion, galaxies that are visible today will eventually move beyond the horizon. Their light, stretched and weakened, will reach us one last time, and then no more will follow. In this sense, the night sky is temporary. The galaxies we see are a gift of timing, visible in this era but not in future ones. Billions of years from now, distant observers will see a far emptier sky. Only the local group of galaxies bound by gravity will remain visible. All others will have receded beyond reach. This paints a sobering picture. Right now, with our instruments, we can see galaxies more than 13 billion years in the past, their light stretched into infrared. We're glimpsing the universe when it was young, when galaxies were just beginning to form, but there are galaxies we will never see, because their light will never reach us. They lie beyond our reach not because of distance alone, but because of the dynamic nature of space. Expansion ensures that there is always more beyond, always regions cut off from us, always galaxies that remain forever unseen. It is strange to think of galaxies in this way, not as unreachable in practice, like distant lands, but unreachable in principle, forever outside the sphere of our knowledge. On Earth, every place can, at least in theory, be reached. You can walk across continents, sail across oceans, fly across the globe. Even planets in our solar system, though difficult, are within the reach of spacecraft. But galaxies beyond our horizon are different. No technology, no matter how advanced, could ever bring them closer. They are separated not by distance alone, but by the expansion of the universe itself. Their inaccessibility is woven into the fabric of reality. This changes how we think about the universe. When we look at deep field images from telescopes, we might imagine we are seeing the whole of existence stretched out before us. In truth, we are seeing only a slice. For every galaxy visible, there are countless more beyond our reach. Our maps of the cosmos, vast as they are still only partial. The unseen outweighs the seen. It also changes how we think about the future. For observers living billions of years from now, the sky will look different. The great clusters and filaments that now fill the cosmos will no longer be visible. The night sky will contain only the merged remnants of the local group. Cosmology itself will become harder. Without galaxies drifting away, without evidence of expansion, future astronomers may not realize the universe is expanding at all. They may believe they live in a static cosmos, unaware of the vast history we can study today. Our era is unique, a window of time when galaxies beyond our reach are still visible, their light still arriving. Galaxies beyond our reach also raise questions about what lies on the other side of the universe. If so many exist that we will never see, then what else might there be? Structures larger than any we can detect. Regions where galaxies are arranged differently, where the density of matter varies, where the story of cosmic evolution played out in unfamiliar ways. We cannot know directly, but the existence of unreachable galaxies guarantees that the universe holds more than we can observe. The other side is not empty, but full, richer than our vision allows. The thought that galaxies slip beyond our reach can feel unsettling, but it can also be seen as a reminder of scale. The universe is not a stage designed for us. It is a vast, evolving structure that follows its own rules. We are lucky to exist at a time when the sky is still crowded, when telescopes can still trace light from the first galaxies. To witness this is to live in a privileged moment, one that future observers will not share. The galaxies we see today are part of our story, even if they will not remain part of anyone else's. This reality also gives urgency to our study of the cosmos. The light reaching us now from distant galaxies may be the last we ever receive. To capture it, to analyse it, to understand it, is to preserve a record that will not exist forever. The observable universe is not only finite in space, but temporary in time. Our moment is one when galaxies beyond our reach are still whispering to us, sending signals across the vastness. To listen now is to honour the fleeting connection. And yet, even knowing that most galaxies are beyond our reach, there is comfort in realising that they exist. The universe is larger, more abundant, more filled with matter and light than we can see. Our inability to touch them does not make them less real. They remain part of the cosmos, shaping its structure, influencing its expansion, existing in their own right. They remind us that reality is bigger than perception, that what lies on the other side of the universe is not defined by us but by itself. When we look at the night sky, every galaxy we see is both a wonder and a reminder. For each one visible, countless more are hidden. The visible galaxies are not the full picture, but only the accessible portion. Beyond them lies a greater cosmos, filled with galaxies forever beyond our reach. They are the silent majority of the universe, unseen and perhaps always unseen, yet shaping the story of everything. Physics is our best tool for understanding the universe. It gives us equations to describe motion, energy, light, matter, and the fabric of space and time itself. From the falling of an apple to the expansion of galaxies, physics offers laws that connect events into patterns, turning mystery into comprehension. Yet for all its power, physics also carries limits. It tells us not only what we can know, but where knowledge must stop. The universe is not simply a collection of answers waiting to be found. It is a place where some questions may never yield, no matter how much progress we make. On one side, physics suggests things with remarkable confidence. We know, for example, that the universe is expanding. Observations of distant galaxies show a redshift in their light, evidence that space stretches between them and us. We know that this expansion is accelerating, driven by dark energy. We know that galaxies cluster in a web-like structure shaped by dark matter. We know that the cosmic microwave background is the cooled remnant of a hot, dense, early phase, a faint glow carrying information about the universe when it was only hundreds of thousands of years old. These are not guesses, but measured facts, supported by data from multiple sources. Physics gives us tools to extract knowledge from signals billions of years old, to reconstruct history from faint whispers of light. Physics also suggests possible futures. With the discovery of accelerated expansion, we can predict that galaxies not bound to us gravitationally will continue to recede until they slip beyond the cosmic horizon. We can estimate that stars will burn their fuel and fade, leaving remnants of white dwarfs, neutron stars, and black holes. Over longer timescales, black holes themselves will evaporate through Hawking radiation, releasing their energy until nothing remains but thin radiation. This is not speculation in the ordinary sense. It follows from the laws of physics as we know them, extrapolated across immense spans of time. At the same time, physics tells us where knowledge must stop. We cannot see beyond the observable universe, because light from those regions has not reached us. Physics assures us those regions exist, governed by the same laws, but direct knowledge is cut off. No matter how perfect our instruments become, no matter how long we wait, there will always be regions permanently unobservable. The universe itself creates a boundary between what can be known and what cannot. Another limit lies in the very beginning. The Big Bang model describes the universe when it was extremely hot and dense, but only after a certain point. As we move back toward time zero, the equations break down. At the Planck time, about 10 to 43 seconds after the beginning, our physics no longer applies. General relativity and quantum mechanics, our two best theories, cannot yet be unified. What happened before that moment, if before even makes sense, is hidden from us. Physics suggests possibilities, like inflation or bouncing cosmologies, but it cannot yet tell us definitively what occurred. This is not a failure of creativity, but a fundamental limitation of current theories. Even within observable space, there are things we may never know. Consider dark matter. We infer its existence from its gravitational effects, but its true nature is still a mystery. Experiments continue to search for direct detection, but it is possible that the particles or phenomena responsible are beyond our reach. We may never build detectors sensitive enough to capture them. Similarly, dark energy is even more elusive. We know it drives accelerated expansion, but whether it is cosmological constant or something more dynamic remains unclear. It may be that its nature cannot be pinned down precisely, that it is woven into the structure of space in ways we can only approximate. There are also limits imposed by chaos and complexity. Physics can describe the laws that govern matter, but in systems with countless interactions, prediction becomes impractical. We know the equations for how fluids flow, but we cannot predict every swirl of turbulence in a river. We know the laws of chemistry, but we cannot forecast the exact path of every molecule in a cloud. On cosmic scales, this means we may know the overall behaviour of galaxies and clusters, but not the precise history of each star or the exact motion of every particle. Physics gives a structure, but it does not erase complexity. Some details are forever beyond reach, not because the laws are unknown, but because the outcomes are too intricate to track. The quantum world introduces another kind of limit. Quantum mechanics allows us to calculate probabilities with extraordinary accuracy, but it does not allow certainty about individual events. We can predict how likely an electron is to be found in a region, but we cannot say exactly where it will be. We can calculate the half-life of a radioactive isotope, but not the exact moment when a particular atom will decay. Physics suggests the patterns but denies the specifics. Knowledge itself is probabilistic, not absolute. This is not a gap in understanding. It is built into the structure of reality as far as we can tell. And then there are the questions of ultimate scope. Is the universe infinite or finite? Does it curve back on itself, or does it stretch endlessly? Physics suggests models, but it also admits that observation may never settle the matter. If the universe is larger than the observable portion by a vast factor, we may never detect its true shape. Similarly, the multiverse remains an open possibility. Physics suggests mechanisms by which multiple universes could exist, through eternal inflation or quantum branching, but whether they are real may never be confirmed. These ideas may remain forever at the border between what physics suggests and what cannot be known. This tension between knowledge and limit is not a flaw in science. It is part of its strength. Physics is honest about what it can and cannot answer. It does not pretend that every question has a solution waiting. Instead, it marks boundaries. It says here is where the data takes us, and beyond this line we do not know. For some, this may feel frustrating, but in another sense it is liberating. It shows that curiosity never ends, that mystery is built into the structure of existence. There is also a human side to this contrast. The things physics suggests are already staggering. The idea that light has been travelling for billions of years, that galaxies formed from tiny fluctuations in the early universe, that space itself is expanding, that black holes slowly evaporate. These are extraordinary insights. They reveal a universe far more surprising and vast than earlier generations imagined. But the things we cannot know are just as meaningful. They remind us that the universe is not small enough to be wrapped neatly in our theories. It remains larger, deeper, and stranger than complete understanding allows. From one perspective, the things we will never know may outnumber the things we can. There will always be galaxies beyond the horizon, regions forever unseen. There will always be scales too small or too complex to measure. There will always be beginnings and endings beyond the reach of current theories. But this does not make our knowledge less valuable. It makes it more precious. To understand even a fraction of the universe is remarkable, given its scale. To know its laws at all is extraordinary. Physics suggests not certainty but wonder, grounded in evidence yet open to limits. In daily life, we rarely think about these boundaries. We live in a world where questions often do have answers. But when you step into cosmology, you step into a domain where limits are built into the fabric of reality. The edge of the observable universe is not a line we can cross with a better telescope. It is a fundamental limit of light and time. The Planck time is not a gap we can fill with cleverness, but a boundary where our best theories collide. Dark energy is not a puzzle missing only one piece, but a reminder that reality may have layers we cannot uncover. Physics is both a lantern and a horizon. So when we ask what physics suggests versus what we can never know, the answer is not simple. Physics suggests a universe expanding, structured by dark matter, accelerated by dark energy, filled with galaxies, stars and planets. It suggests laws that hold everywhere, equations that describe motion and energy across scales. It suggests a future where galaxies drift apart, stars burn out and black holes evaporate. But it also shows us the limits. It shows us that some regions are forever unreachable, that some moments in time are forever hidden, that some questions may never yield. Both sides are part of the same truth. Physics illuminates, and it defines the shadows where illumination cannot go. When most people think about science, they imagine precision, numbers, experiments and evidence. They picture scientists in labs, careful and cautious, measuring and testing. Science, in this view, is the opposite of imagination. It is grounded, practical, skeptical, bound by data. And in many ways that is true. Science thrives on evidence. A claim without support is not accepted. Observations, measurements and repeatable experiments form the backbone of every advance. Yet what is less often appreciated is that imagination plays just as essential a role. Without imagination, science would not move forward at all. Every discovery begins with a question. Why does an apple fall? Why do the planets move the way they do? Why does light behave both like a wave and a particle? Each question requires imagination to even be asked. It requires the ability to see beyond what is obvious, to picture alternatives, to wonder whether reality could be different than it appears. Imagination is the spark that sets the process in motion. Data may guide the answer, but imagination frames the question. Consider Einstein. His breakthroughs in relativity did not come from experiments alone, but from thought experiments, exercises of imagination. He pictured himself riding on a beam of light, or watching two lightning strikes from different moving trains. By imagining these scenarios, he uncovered the relativity of time and space. The equations followed, but only after imagination had broken the ground. Without that leap of thought, the discoveries would not have come. The same is true for quantum mechanics. The early pioneers faced phenomena that made no sense in classical terms. Electrons behaving like waves, particles tunneling through barriers, probabilities replacing certainties. To make sense of this, scientists had to imagine new frameworks, worlds where reality itself behaved differently. They argued, debated, and constructed models that stretched the limits of what they could picture. The theories that emerged were not simply calculations. They were products of imagination tested against experiment. In cosmology, imagination is even more visible. The idea that the universe is expanding, that it began in a hot, dense state, that it is filled with invisible matter and driven by dark energy. None of these are obvious. They are products of creative thinking, guided by data but not dictated by it. When Edwin Hubble observed galaxies receding, It required imagination to propose that space itself was stretching. When scientists mapped the cosmic microwave background, it required imagination to see it as the afterglow of the Big Bang. Without imagination, the data would have remained unexplained. Even the search for what lies on the other side of the universe is an act of imagination. No telescope can yet show us beyond the observable horizon, yet scientists imagine possibilities. Infinite space, curved space, multiverses, hidden dimensions. These are not fantasies but carefully constructed ideas, grounded in mathematics and theory, waiting for evidence to confirm or refute them. Imagination allows scientists to think beyond the data they have, to construct models that explain and predict, to propose what might be true. Imagination is also essential because science advances into the unknown. If we only ever worked with what is already known, progress would stop. To explore, scientists must picture what cannot yet be seen. They must imagine new particles, new forces, new structures. Sometimes these imagined entities turn out to be real, like the Higgs boson, predicted long before it was detected. Sometimes they turn out to be wrong, like the ether once thought to carry light waves. But even when wrong, imagination is not wasted. It frames experiments, tests possibilities, and clears the way for better ideas. This is why imagination in science is not the same as pure invention. It is disciplined imagination. It is not free-floating fantasy, but structured creativity. Scientists imagine possibilities and then test them. They imagine patterns and then look for evidence. Imagination and evidence work together, each incomplete without the other. Evidence without imagination is sterile, data without meaning. Imagination without evidence is speculation, untethered from reality. Together they form the method of science, the balance of creativity and rigour. The role of imagination can also be seen in technology. Every invention begins as an idea, a vision of what could exist. Airplanes, computers, spacecraft, all were imagined before they were built. The laws of physics set boundaries, but imagination finds possibilities within those boundaries. To put a telescope in orbit required imagining what it could show. To send a rover to Mars required imagining landscapes never seen. To design a detector for dark matter requires imagining particles that may or may not exist. Every step forward depends on this act of picturing the unseen. Imagination also bridges the gap between scales. On one end, quantum mechanics deals with particles too small to picture directly. On the other, cosmology deals with distances too vast to comprehend. In both cases, imagination helps. We imagine electrons as waves, galaxies as dots in a web, space itself as stretching. These pictures are imperfect, but they guide understanding. They give form to abstractions, allowing us to reason about the unobservable. Without imagination, the equations would remain symbols without meaning. It is worth noting, too, that imagination in science is collective. No single scientist holds all the answers. Ideas are proposed, challenged, refined, discarded, or expanded by the community. One person imagines a possibility, another tests it, another imagines an alternative. The progress of science is a dialogue between many imaginations filtered by evidence. Theories grow not from one mind alone, but from the interplay of many. Imagination is contagious, spreading from paper to paper, from lecture to lecture, inspiring new questions and new approaches. This interplay of imagination and evidence also explains why science never ends. No matter how much we discover, new questions appear. Each answer opens a new horizon. To imagine what might lie beyond that horizon is the first step toward the next discovery. As long as curiosity exists, imagination will find ways to stretch science further. There will always be questions about what lies beyond, about what the other side of the universe holds. Imagination ensures those questions are asked, even when evidence has not yet arrived. At the same time, science must always balance imagination with humility. Not every imagined idea will turn out to be true. History is filled with theories that seemed promising but were later set aside. The strength of science lies in this willingness to let go, to allow evidence to decide. Imagination is the beginning, not the end. Theories are tools, not certainties. The universe is under no obligation to match what we picture. Imagination stretches toward reality, but reality always has the final word. For those who practice science, this balance is part of the daily work. It is not only about collecting data, but about imagining what that data could mean. It is not only about solving equations, but about picturing the scenarios they describe. It is not only about confirming old ideas, but about daring to propose new ones. Imagination is the quiet partner in every discovery, present in every leap forward, shaping how questions are asked and how answers are interpreted. From a wider perspective, the role of imagination in science is also deeply human. It connects science to art, literature, and philosophy. All are driven by the same impulse to imagine what is beyond the obvious, to picture what cannot yet be seen, to create patterns of meaning. Science grounds imagination in evidence, but the impulse is the same: to wonder about the other side of the universe, to picture it in equations or in stories, is an act of imagination shared across disciplines. It shows that curiosity is not only rational, but creative, not only logical, but imaginative. So when we ask what lies beyond the universe, we are not only asking a scientific question, we are engaging imagination itself. Physics gives us models, but imagination gives us the courage to consider them. Evidence narrows the possibilities, but imagination opens them. The other side of the universe may remain beyond observation, but it is not beyond imagination. And in that sense, imagination is not only a tool of science, but a way of keeping the universe alive in our minds, even where knowledge ends. When people hear about the limits of the universe, the first reaction is often to think that those limits are far away, distant horizons that do not affect daily life. The observable boundary lies tens of billions of light years away. The expansion of space and the mysteries of dark energy seem abstract. The breakdown of physics at the Planck time feels remote. But the truth is that the limits of the universe shape us in ways both direct and subtle. They define not only how far we can see, but how we live, how we think, and how we imagine ourselves in the world. The most obvious way the universe's limits shape our lives is through time. We live in a cosmos with a beginning. The Big Bang is not just a theory about the distant past. It is the reason why stars exist at all. In a universe without a hot, dense beginning, matter would never have coalesced, galaxies would never have formed, stars would never have lit. Our very existence depends on the boundary that separates a time before stars from a time after. We live downstream of a limit, one that made possible every atom in our bodies. The finite speed of light is another limit that shapes our lives constantly. Light takes time to travel, and that delay defines how we experience the world. When you look at the sun, you see it as it was 8 minutes ago. When you look at the stars, you see them as they were years, centuries, or millennia in the past. Our perception of the universe is always a step behind reality, always filtered by time. This is not just a curiosity, but a condition of existence. The universe has built into it a speed limit for information. It means we never see things as they are, only as they were. It gives us history with every glance upward, reminding us that the present is always stitched together from the past. Gravity itself is a limit that shapes our lives. It holds us to the Earth, shapes the orbit of our planet, and sets the conditions for life. But it also prevents us from reaching beyond too easily. To leave Earth requires immense energy. To reach even the nearest star would take thousands of years with current technology. The limit imposed by gravity and distance defines our place. It keeps us local, rooted in one corner of the cosmos. Our dreams of travel to other stars or galaxies exist within the awareness that those journeys are bounded by the laws of physics. The limits of the universe remind us daily that we live in a particular place, a specific neighbourhood. one that cannot be escaped without extraordinary effort. There is also the limit of mortality, tied to cosmic limits in profound ways. Stars are not eternal, they burn and die. Our sun, for example, has a finite lifetime. In billions of years it will expand, burn hotter, and eventually shed its outer layers, leaving behind a white dwarf. Life on Earth is tied to this timescale. Our existence is not only shaped by cosmic beginnings, but by cosmic endings. The limits of stars dictate the limits of life. The same cycles that created us also guarantee that nothing lasts forever. Even the existence of dark matter and dark energy, as abstract as they sound, shape our lives. Dark matter, by holding galaxies together, made possible the long-term stability required for stars and planets to form. Without it, the Milky Way would not exist. Dark energy, by accelerating expansion, determines the ultimate fate of the cosmos, a fate that includes us because we are part of it. These unseen forces remind us that most of what shapes our world is invisible. The universe's limits are not always visible at first glance, but they form the scaffolding of existence. The psychological impact of the universe's limits is just as powerful. To know that we cannot see beyond the observable horizon changes how we think about reality. It humbles us, reminding us that what we know is only a fragment. At the same time, it inspires imagination, pushing us to wonder about what lies beyond. The very limit creates the desire to reach past it, even if only in thought. Without the boundary, we might not ask the question. The horizon, unreachable though it is, keeps curiosity alive. This also applies to the ultimate unknowables in physics. The fact that we cannot see before the Planck time does not end the story. It sparks new theories, from inflation to multiverses to bouncing cosmologies. The limit does not silence us. It provokes us. In this way, the limits of the universe are not dead ends but starting points. They push thought forward, guiding how science evolves. Our lives, our cultures, and our imaginations are shaped by these limits because they frame the questions we ask. There is also comfort in limits. Infinity can be overwhelming. To live in a universe with no boundaries, no beginning, no structure, might feel disorienting. Limits give form. A beginning gives us a story. Horizons give us a sense of scale. The speed of light gives us order, preventing chaos in how events unfold. The universe's limits are not only constraints but structures. They shape meaning as much as they shape reality. On a more intimate level, the universe's limits influence how we think about time and mortality. Knowing that stars live and die reminds us of our own cycles. Knowing that galaxies move beyond reach reminds us that moments slip away. We live in a universe of impermanence, where nothing lasts forever. Yet this impermanence also gives value. The fleeting nature of stars, planets, and lives makes them precious. If the universe were without limits, perhaps we would not treasure moments as we do. The boundaries shape our sense of meaning. The limits of the universe also connect us to one another. Every person, no matter where they live, looks up at the same horizon. We all share the same cosmic boundary. The light from distant galaxies reaches all of us. The mysteries of dark matter and dark energy puzzle all of us. The limits of knowledge are universal. They form a common ground across cultures and generations. In this way, the universe's limits do not separate us but unite us. They remind us that we're all participants in the same story, bound by the same horizons. It is easy to think of limits as negative, as things that prevent us from going farther. But in truth, limits give shape to possibility. Without gravity, stars and planets would never have formed. Without the speed of light, causality would collapse. Without beginnings and endings, there would be no cycles, no evolution, no change. Limits create structure. They make the universe what it is. Our lives, far from being diminished by limits, are made possible by them. In a practical sense, the universe's limits also guide how we build knowledge. We know we cannot see beyond the horizon, so we focus on what we can observe. We know we cannot measure before the Planck time, so we refine theories to approach it. We know we cannot travel beyond the nearest stars, so we build probes and telescopes to extend our reach in other ways. The limits set the stage for human ingenuity. They define the boundaries within which creativity works. Every discovery we make is shaped by the awareness of where the walls are. And finally, the universe's limits shape our imagination of what might lie beyond. By setting boundaries, they invite speculation. The horizon makes us wonder about other galaxies, other universes, other dimensions. The unknown before the Big Bang makes us consider alternative origins. The fading of galaxies beyond reach makes us imagine futures different from the present. Limits keep us from seeing everything, but in doing so they ensure we never stop asking. The universe's limits shape our lives not only by constraining us, but by keeping curiosity alive. So while the boundaries of the cosmos may seem distant, they are woven into everything we do. They define the conditions for life, shape the course of science, influence our sense of time and meaning, and connect us through shared mystery. To live in this universe is to live with limits, and far from being a disappointment, those limits give structure to existence, a frame for wonder, and a reminder that what we know is always just a part of the whole. When we talk about the infinite, it often feels like something far away, abstract, or mathematical. Infinity belongs to numbers on a page, to equations that stretch without end, to distances too large to picture. But the infinite is not only out there beyond the galaxies, in a way, it circles back to us. To think about what lies on the other side of the universe is also to think about who we are, how we perceive, and what it means to exist within something so vast. The journey outward into the infinite always leads back inward, into questions about ourselves. One of the first ways this happens is through perspective. When we look at the universe, we imagine ourselves as small, a single planet around an average star in one galaxy among billions. Against that scale, the infinite seems overwhelming, reducing us to insignificance. But if we shift perspective, the infinite also highlights our uniqueness. Out of all possible arrangements of matter, here we are, conscious beings able to ask questions about the universe. The very act of wondering is a way of locating ourselves within infinity. It is not just a vast cosmos out there. It is a vast cosmos that produced minds capable of imagining it. This connection between the infinite and the personal is not new. Ancient cultures, as we saw, often linked the heavens with stories about life, death, and meaning. The infinite sky was never only about distance. It was always about connection, a backdrop against which human life unfolded. Today, science replaces myth with measurements, but the effect is similar. To talk about infinity is to confront what it means to be finite. To talk about galaxies beyond reach is to ask what kind of lives we live within reach. The outward journey becomes a mirror for the inward. The infinite also circles back to us through time. The universe may stretch endlessly in space, but our time here is brief. Stars live for billions of years, galaxies evolve for even longer, but our lives span only decades. Against infinity, this seems like almost nothing, and yet, in that small time, we can grasp ideas that span billions of light years. Our minds compress the infinite into thoughts we can hold. We cannot live as long as stars, but we can imagine their lifetimes. We cannot travel across the cosmos, but we can picture its expansion. In this sense, the infinite is not just something beyond us. It is something we bring into ourselves through thought and imagination. There is also a paradox here. The more we learn about the universe, the more we see its infinite aspects. Unreachable galaxies, endless horizons, possibilities of multiverses. And yet, the more infinite it seems, the more it pushes us to focus on the finite moments we actually have. If galaxies will drift beyond view, then the ones we see tonight are precious. If stars burn for billions of years while we live for only a short span, then the brief time we share under them gains value. The infinite highlights the finite, not to diminish it, but to frame it. Our smallness becomes part of the story, not an error in it. The infinite also leads us back to questions of meaning. Science explains mechanisms, but it cannot dictate significance. When we hear that the universe may be infinite, the question becomes not only what that means for galaxies, but what it means for us. Does infinity make life trivial, because there could be countless versions of it? Or does infinity make life profound, because even in an endless expanse this moment exists once, here, with us? These questions are not answered by physics alone. They are personal, reflective, and philosophical. The infinite does not remove meaning. It demands that we shape it ourselves. There is a psychological dimension to this journey as well. Infinity can create awe, a feeling of vastness that humbles and inspires. Studies of the overview effect, reported by astronauts who see Earth from space, describe a sense of connectedness and wonder that changes how they view life. Looking at the infinite sky can trigger something similar. It reminds us that boundaries are temporary, that we are part of something much larger. This awe is not only about stars and galaxies, it is about ourselves, our ability to sense and feel within a universe that dwarfs us. The journey outward becomes a journey inward, into our own capacity for wonder. Imagination plays a central role here. Infinity is not something we can experience directly. We cannot walk across it or touch it, but we can imagine it. Every time we picture what lies beyond the horizon, every time we wonder about galaxies forever unseen, we bring infinity into our minds. This act of imagination connects us to the cosmos in a way no telescope alone can. Instruments extend our senses, but imagination bridges the gap between data and meaning. To think about infinity is to stretch the mind, to test the limits of thought itself. In doing so, we discover not only more about the universe, but more about ourselves. The infinite also returns us to ourselves through community. Everyone shares the same cosmos. No matter where someone lives, they see the same stars, the same sky, the same horizon. The infinite is not private. It is universal. When we look at it, we are connected to every other human who has ever looked upward. This shared experience shapes culture, history, and identity. The infinite out there becomes part of the infinite connections among us. The journey outward is mirrored by the journey toward one another, bound by common awe. And then there is the future. Infinity reminds us that our place in time is fleeting, but it also reminds us that life may continue, that exploration may go on. We may not reach other galaxies, but perhaps distant descendants will. We may not solve all mysteries, but perhaps others will. Infinity ensures that the story is not finished. It continues beyond us. This does not make our part meaningless. It makes it part of a larger whole. To see ourselves in infinity is to see ourselves as participants in an ongoing journey, one that began long before us and will continue long after. Even in the most personal sense, infinity touches our lives. When we think about choices, possibilities, and paths not taken, we imagine versions of ourselves that might have been. In this way, infinity enters our psychology. It is not only about galaxies and light years, but about the branching possibilities of life. Just as physics imagines parallel realities, we imagine alternate versions of ourselves. The infinite in science mirrors the infinite in thought. Both circle back to the same question. Who are we in all this vastness? And maybe that is the deepest point. The infinite is not something separate from us. It is something we are inside of, something we participate in. Every atom in our bodies was forged in stars. Every thought in our minds is shaped by the limits and possibilities of physics. Every question we ask about the other side of the universe is, in the end, a question about ourselves. The journey outward, to the farthest galaxies, to horizons we cannot cross, to infinite possibilities, always loops back inward. It reminds us that to understand the universe is to understand our place within it. So when we speak of infinity, we are not only describing a mathematical concept or a physical possibility, we are describing the context in which we live, the background against which our lives unfold. Infinity is the canvas, and we are the patterns on it. The journey into infinity is also the journey into ourselves. It shows us that even in a universe without edges, we have boundaries. Even in a cosmos beyond measure, we measure our days. Even in endlessness, we find meaning in the finite. Thank you for being here until now. We've travelled far together, through horizons we cannot see, through galaxies beyond our reach, through the invisible world of dark matter and dark energy, through ideas of parallel realities and infinite space. Each step has taken us farther outward, and each step has also turned us quietly back inward. Now, as we come to rest, we arrive not at answers but at mystery. The mystery has been with us all along, woven into every question about what lies on the other side of the universe. And perhaps the best way to close is not by trying to solve it, but by allowing ourselves to rest within it. Mystery in science is not a failure. It is a condition of the universe itself. There will always be horizons we cannot cross, not because we lack effort, but because reality itself sets boundaries. Light takes time to travel, and there will always be regions beyond its reach. Physics breaks down at the earliest moments, and there may always be aspects of beginnings that remain hidden. Dark matter and dark energy remind us that most of reality is unseen. Infinity reminds us that the vastness may never be fully mapped. These are not shortcomings of human knowledge. They are part of the structure of existence. To rest in the mystery means accepting that the unknown is not a problem to solve immediately. It is a companion, a constant presence that shapes how we live and think. The horizon is not an obstacle but a frame. The unseen is not emptiness, but abundance waiting beyond reach. When we accept a mystery, we allow curiosity to remain alive without needing closure. We accept that questions may last longer than lifetimes, that wonder is as valuable as certainty. This is not only true in science. In life itself, mystery surrounds us. We do not always know why events happen the way they do, why choices lead to certain paths, why some things endure and others fade. The same limits that shape the cosmos shape our personal lives. We live within horizons, within finite time, within boundaries of understanding. To rest in the mystery is to acknowledge that this is not a flaw but a truth. It is what makes moments precious, what makes curiosity meaningful, what makes being alive remarkable. Science, for all its rigour, is built on this acceptance. Every great discovery begins with a question that acknowledges mystery. Astronomers did not start with the knowledge of galaxies beyond the Milky Way. They started with faint smudges of light, mysterious and unexplained. Physicists did not start with dark matter and dark energy. They started with anomalies, galaxies rotating strangely, the universe expanding faster than expected. The mystery was not an end, it was the beginning. It was the reason to look deeper, to imagine more, to build better instruments. So when we close our journey here, the destination is not a final answer, but a recognition of how important it is to keep mystery close. It is what drives curiosity forward, what keeps us asking questions. It is also what gives science its humility, reminding us that reality is larger than any theory. The universe is not here to be wrapped neatly into conclusions. It is here as an open field, wide and vast, with limits that shift as we learn, with questions that deepen as we look. There is comfort in this. If everything were already explained, if no mystery remained, curiosity would lose its spark. Instead, we live in a universe where every horizon invites another question, where every answer opens a door to something larger. The mystery is not a gap to be closed, but a space to dwell in. To rest in it is to let go of the need to finish the story, and instead enjoy being part of it as it unfolds. This perspective brings us back to where we began, with you lying or sitting quietly, listening reflecting, perhaps drifting. The question of what lies on the other side of the universe may never have a final answer, but it does not need one. The asking is enough. The act of wondering is itself a connection, a bridge between the small and the infinite. Each time you look up at the stars, you're participating in the oldest mystery humanity has known. You're adding your curiosity to the countless others who have looked upward before you. And in this moment, as the day fades or the night deepens, you do not need to solve the mystery. You can let it surround you. The galaxies, the horizons, the invisible forces, they all continue, vast and quiet, whether or not you understand them fully. The universe does not demand answers from you. It offers itself as it is, open and expansive, waiting in silence. To rest in the mystery is to accept that silence, to breathe with it, to feel its presence without pressing for more. This rest is not the end of curiosity, it is part of its rhythm. Curiosity expands outward, seeking, questioning, imagining. Then it pauses, returns inward, and rests in the wonder of what is not yet known. This rhythm is natural, like the tide. It does not diminish discovery, but sustains it. Without rest, curiosity burns out. With rest, it gathers strength for the next horizon. Tonight, the mystery is enough. Tomorrow, the questions will come again. And so we close not by leaving the mystery behind, but by carrying it with us. The other side of the universe remains unknown. It may always remain unknown. But that unknown is not emptiness. It is possibility. It is space for imagination, for science, for wonder, for connection. It is what gives meaning to the stars you see and the thoughts you hold. The other side of the universe is also the other side of yourself, the place where questions remain, where curiosity lives, where wonder never ends. For now, you can let it be. Let the mystery settle around you like the night sky, wide and calm. Let it be a space for rest, for peace, for quiet awe. The universe is vast. You are part of it. And within that balance of smallness and belonging, you can rest, knowing that the mystery is not something to escape, but something to embrace. Thank you for sharing this time and space with me. If you found these thoughts soothing, or if you'd like to drift through more journeys like this, you're always welcome here. You can subscribe, or simply return whenever you'd like, and together we'll keep exploring quietly, step by step, without hurry. For now, close your eyes if you wish, let the mystery hold you, and rest deeply.